What if everything you thought you knew about gravity was only half the story? Think about that sensation you feel every single day. The gentle but persistent pull that keeps you anchored to the Earth. The same force that guides the Moon in its silent dance around our planet and holds entire galaxies together. For centuries, we've accepted gravity as one of the universe's fundamental forces, something simple, almost obvious in its presence. But what if it isn't fundamental at all? What if gravity, in all its cosmic grandeur, is something far stranger and more marvelous, an illusion emerging from a hidden quantum world? Imagine a universe where gravity isn't a force in the traditional sense, but rather a kind of cosmic tapestry woven from the invisible, vibrating threads of quantum fields. These fields are not empty voids. They're dynamic, energetic, and filled with activity even in what we call nothingness. Fluctuations at the quantum level, spontaneous, unpredictable, and deeply mysterious, may be secretly generating what we perceive as gravity. It's an idea that turns physics on its head, suggesting that the anchor of our reality is not a primitive pull but a sophisticated side effect of something deeper. This is where our journey begins, with a startling revelation that gravity, the most familiar yet least understood of all forces, might be concealing its truest nature within the subatomic realm. In this video, we'll unravel 38 astonishing secrets encoded in quantum fields, clues that could finally piece together the puzzle of gravity itself. We'll explore how these insights don't just fill gaps in our knowledge. They challenge the very framework of reality, bridging the monumental divide between Einstein's theory of relativity and the quantum mechanics that governs the tiny. From the holographic principle to quantum entanglement, from emergent space-time to the role of information itself, each secret opens a door to understanding not only why gravity works but what it truly is. And this isn't just theoretical. It could reshape future technologies, redefine our place in the cosmos, and bring us closer than ever to unlocking the universe's greatest enigma. So join us as we step into the heart of one of science's most profound mysteries, where every discovery invites more wonder, and every answer reveals a deeper question. Our journey into gravity's quantum secrets begins not in the abstract, but with a story you likely know, the tale of Isaac Newton and a falling apple. That moment of inspiration in the 1660s gave us the first mathematical law of universal gravitation, a force that pulls apples to the ground and planets around the sun with predictable, clockwork precision. Newton's genius was to describe the what of gravity with stunning accuracy, framing it as an invisible, instantaneous force acting across vast distances. His equations worked beautifully for centuries, enabling us to predict tides, launch satellites, and understand orbital mechanics. Yet this powerful theory contained a deep and troubling mystery. How does gravity actually work? What is the mechanism that allows the Sun to reach across 93 million miles of empty space to hold Earth in its embrace? Newton himself was deeply unsettled by this, famously writing, "I frame no hypotheses about the cause of this mysterious action at a distance." His theory described the pull but left the rope itself completely invisible. This profound gap in our understanding persisted for over 2 centuries until a young patent clerk in Switzerland reimagined the very stage upon which the universe plays out. Albert Einstein's theory of general relativity, published in 1915, was a monumental paradigm shift. He proposed that gravity is not a force pulling through space, but rather the geometry of spacetime itself. Imagine the universe not as a static stage but as a flexible, stretchy trampoline. A massive object like the Sun creates a deep dimple in this fabric, and Earth simply follows the curved path around that dimple. It's not being pulled. It's rolling along a groove in the cosmic landscape. This elegant idea solved the mystery of how gravity works. replacing the spooky action at a distance with the beautiful warping of space-time. It made stunning predictions that were later confirmed, from the bending of starlight by the sun to the existence of black holes and gravitational waves. Yet for all its brilliance, Einstein's theory created a new and even grander puzzle. General relativity is a classical theory, describing the smooth, deterministic curvature of spacetime on a large scale. Meanwhile, the other three fundamental forces of nature, electromagnetism, and the strong and weak nuclear forces, are perfectly described by the chaotic, probabilistic rules of quantum mechanics. This created a great schism in physics. We have two incredibly successful but utterly incompatible rulebooks for the universe, one for the very big and one for the very small. The force that shapes the grand cosmos refuses to play by the same rules as the forces that govern its fundamental particles. This conflict becomes most apparent in extreme environments like the singularities at the hearts of black holes or the first moments of the Big Bang, where immense gravity meets tiny quantum scales. Here, the equations of both theories break down, yielding nonsensical answers of infinite density and curvature, screaming for a deeper, unified understanding. This historical context is not just a lesson in physics. It's the essential setup for our exploration of the 38 secrets. Each previous theory was a revolution that explained the phenomena of its time, but ultimately pointed toward a deeper truth waiting to be uncovered. Newton's force pointed to Einstein's geometry. Now, Einstein's geometry points directly to the quantum field. The gaps and paradoxes left by general relativity are not failures. They are the precise clues that guide us toward the next great revolution. They show us that gravity cannot be a standalone force but must be emergent, a collective phenomenon arising from the frenetic dance of quantum fields. Understanding this historical puzzle allows us to see that these 38 secrets are not minor tweaks but potential keys to the final lock, offering a vision of gravity not as a primitive force, but as a masterpiece woven from the hidden threads of the quantum world. So if Einstein's curved spacetime gives us the stage, then quantum fields are the actors upon it, the fundamental, dynamic entities that make up everything in the universe. To grasp the secrets that follow, we first need to understand what a quantum field truly is. Forget thinking of the vacuum of space as an empty, silent void. Instead, envision it as a vast, restless ocean. Even on the calmest day, the ocean's surface is never perfectly still. It's alive with tiny ripples, waves, and spontaneous movements. That's the quantum vacuum. It is not empty. It is a seething, bubbling sea of energy, filled with invisible fields that stretch across all of space and time. Every fundamental particle we know, every electron, every quark, every photon of light, is not a tiny, solitary speck, but rather a localized excitation, a kind of concentrated vibration in its respective quantum field. Think of it like this. Imagine a perfectly still mattress. That's the field in its ground state. Now give one spot a firm tap. A wave travels out from that point. That wave is a particle. The electron field fills the universe, and when it vibrates in just the right way, we detect an electron. The electromagnetic field vibrates, and we get a photon. You and I, and everything we see, are not just made of particles, but are intense, complex vibrations in a cosmic symphony of fields. This is the first monumental shift in perspective. Particles are not in the field, they are the field. And these fields are inherently quantum, which means they behave in ways that defy our everyday intuition. They exist in a state of superposition, meaning a field can be in multiple states or configurations simultaneously until we interact with it and force it to choose a specific value. This is the famous Schrödinger's cat paradox, but applied to the fabric of reality itself. Furthermore, these fields can become entangled. Two particles born from the same interaction remain deeply connected, their fates intertwined no matter how far apart they travel. A change to one instantly influences the other, not by sending a signal through space, but because they are part of a single, unified field description, a connection that seems to operate outside of spacetime itself. This leads us to one of the most fascinating consequences: quantum fluctuations, due to the Heisenberg uncertainty principle, which states that we can never precisely know both a particle's energy and its location at the same time. These fields are constantly fluctuating. Even in a perfect vacuum at absolute zero, the fields are jittering. This constant motion creates a frothing sea of what we call virtual particles, short-lived pairs of particles and antiparticles that spontaneously pop into existence, borrow energy from the vacuum for an incredibly brief moment, and then annihilate each other, returning the energy almost immediately. This isn't just theoretical. We can observe the effects of this quantum foam. It's responsible for the Casimir effect, where two metal plates placed incredibly close together in a vacuum are subtly pushed together because the constant dance of virtual particles outside the plates is more vigorous than the limited fluctuations between them. This vibrant, energetic picture of quantum fields forms the absolute bedrock of modern physics. The Standard Model, our most successful theory of particles and forces, is entirely a theory of quantum fields. It describes how these fields interact, exchange energy, and give rise to the rich complexity of our universe. But notably, gravity and general relativity have stubbornly resisted being incorporated into this quantum field framework. This dissonance is our biggest clue. The 38 secrets we are about to explore all stem from asking one profound question. If everything else is a manifestation of quantum fields, could gravity be one too? Is the curvature of spacetime itself perhaps a large-scale, collective effect emerging from the chaotic, probabilistic dance of these fundamental fields? The stage itself may be made of the same actors. Now, let's dive into the very first and perhaps most mind-bending of these 38 secrets, the revolutionary idea that gravity is not a fundamental force at all. For generations, we've placed gravity on a pedestal alongside electromagnetism and the nuclear forces as one of nature's basic, irreducible ingredients. But this secret proposes something far more astonishing: that gravity is an emergent phenomenon. It doesn't exist at the most fundamental level of reality, but instead arises or emerges from the collective behavior of something deeper, the intricate dance of quantum fields. To understand emergence, think about a concept we all know well: temperature. If you hold your hand near a warm cup of coffee, you feel heat. But what is temperature, really? If you could zoom in to the molecular level, you wouldn't find a thing called temperature floating around. Instead, you'd see a chaotic storm of water molecules jiggling, vibrating, and crashing into each other at tremendous speeds. Temperature is not a fundamental property of any single molecule. It is a collective, statistical property that emerges from the average kinetic energy of trillions upon trillions of molecules. It's a shorthand description for the overall behavior of a vast system. In exactly the same way, this secret suggests that the force of gravity may be a kind of cosmic temperature, a large-scale effect that emerges from the microscopic, frantic vibrations of quantum fields. This radical perspective is powerfully articulated in a theory known as entropic gravity, pioneered by Dutch theoretical physicist Erik Verland. He proposes that gravity is essentially a consequence of information and entropy. Now, entropy is a concept from thermodynamics often described as a measure of disorder, but a more precise modern view defines it as a measure of information specifically, the number of ways the microscopic components of a system can be arranged while still looking the same from the outside. Verland's groundbreaking work suggests that what we perceive as gravity is actually a force that drives systems toward higher entropy. It's not a fundamental pull but a statistical tendency, much like how air moves from a high-pressure area to a low-pressure area. It's not being pulled, It's just flowing toward a state of higher probability. Here's a way to visualize it. Imagine the universe is made of countless tiny bits of information, like cosmic pixels. These bits are encoded on the boundaries of space, perhaps on a holographic screen. Now, when you place an object like a planet into this space, it disrupts the arrangement of these information bits. The system wants to maximize its entropy, to find the most statistically likely arrangement of this information. This tendency to reorganize and reach a state of higher disorder manifests itself as a force we have always called gravity. The planet isn't actively pulling on things. Instead, objects move toward it because that's the direction in which the entropy of the underlying quantum information increases. This turns our entire understanding of cause and effect in the universe inside out. Gravity isn't the cause of the phenomenon, it is the phenomenon. It is the thermodynamic gradient of information itself. The staggering implication of this idea is that if gravity is emergent, then space-time, the very stage of reality that Einstein described as curved and dynamic, might also be derivative. Space-time itself may not be the foundation of the universe, but could instead be a kind of illusion, a convenient construct that arises from the interactions of more fundamental quantum components. Think of it like the surface of a lake. The water seems smooth and continuous from a distance, but up close, it's made of individual molecules. The smooth surface is an emergent property. In this view, the smooth, continuous geometry of spacetime emerges from the quantum information of fields. This doesn't make Einstein wrong. In fact, his equations of general relativity emerge perfectly from this more fundamental description, much like the laws of thermodynamics emerge from statistical mechanics. His genius captured the how magnificently, but entropic gravity might finally be revealing the why. If the idea of gravity emerging from quantum information sounded strange, then prepare for a concept that stretches the imagination even further. The possibility that our entire three-dimensional universe, with all its depth and richness, might be nothing more than a magnificent projection, a cosmic hologram. This is the heart of the second secret, the holographic principle. It suggests that all the information needed to describe everything within a volume of space, every star, every planet, every person, could actually be encoded on a two-dimensional surface bounding that space. Our vivid, 3D reality in this view is a kind of illusion, and gravity may be the fundamental mechanism that translates that flat, encoded data into the world we experience. To grasp this, consider an ordinary hologram like the kind you might see on a credit card. A hologram is a flat, two-dimensional surface, but when you shine a light through it, it projects a fully three-dimensional image that you can look around. The crucial point is that every piece of the 3D image is contained in some form within the information on the 2D surface. The holographic principle applies this same logic to the entire universe. It proposes that the boundary of a region of space, for instance, the spherical surface surrounding a black hole's event horizon, acts like that holographic film. It contains a complete description of everything within that volume. The quantum fields we've been discussing are the artists. They are what encode this information. And what we perceive as the force of gravity could be the physical manifestation of the process that decodes this information, translating a 2D blueprint into our 3D reality. Gravity, in this sense, isn't pulling things together. It's the interpreter of the cosmic code. This revolutionary idea didn't come from nowhere. It emerged from one of the most perplexing puzzles in modern physics, the black hole information paradox. As Stephen Hawking discovered, black holes are not completely black. They slowly evaporate by emitting what's now called Hawking radiation. This radiation appears to be purely thermal, random noise containing no information about the specific matter that originally fell into the black hole. This presents a catastrophic problem for quantum mechanics, which holds that information can never be truly destroyed. If you burn a book, you could theoretically recover the information from the smoke and ashes. But if a black hole evaporates completely, it seems the information within it is lost forever, violating a core principle of physics. The holographic principle resolves this paradox beautifully. It suggests that all the information about the objects that fell into the black hole is not lost inside it, but is instead perfectly preserved, encoded on the black hole's two-dimensional event horizon, its outer boundary. As the black hole evaporates, this information can slowly and subtly be released back into the universe through the Hawking radiation. The information was never truly gone, it was just stored on a surface, waiting to be read. This insight provides a breathtakingly unified framework for gravity and quantum mechanics. In the holographic description, a theory of gravity operating in a three-dimensional volume of space is completely equivalent to a quantum field theory operating on the two-dimensional boundary of that space. This is a specific mathematical duality known as the AD-S/CFT correspondence. This means that the immensely complex, non-intuitive problems of quantum gravity, like what happens at the singularity of a black hole, can be translated into problems within a well-understood quantum field theory that has no gravity at all. It's like having a universal translator for the cosmos. Physicists can use the rules of quantum fields on a surface to perfectly understand the behavior of gravity in a volume. This doesn't just bridge the gap between quantum mechanics and gravity. It suggests they are two different languages describing the exact same reality. So what does this mean for you, right here and now? It challenges our most basic assumptions about existence. The solidity of the floor beneath your feet, the vast distance to a star, the three-dimensional world you navigate every day. All of it might be a spectacularly detailed projection. The true action, the fundamental workings of the universe, could be happening on a distant, two-dimensional surface at the edge of the cosmos. Gravity is the force that makes this projection coherent and consistent, the rule that ensures the holographic movie of our universe plays smoothly without glitches. It is the ultimate glue, not of matter, but of information, weaving a 2D data set into the rich, tangible, 3D experience we call reality. But if the holographic principle redefines the stage of reality, then the next secret takes us deep into the very materials from which that stage is built, revealing a subatomic chaos that might be the true source of gravity itself. To peer into this realm, we must venture down to scales a billion times smaller than an atomic nucleus, to a domain where the very concepts of here and now break down into a frenzied, turbulent storm. This is the world of quantum fluctuations, and it gives rise to what physicist John Wheeler poetically called space-time foam. Imagine the tranquil surface of that quantum field ocean we discussed earlier. Now, instead of gentle ripples, picture it during a hurricane, a violent, churning chaos where bubbles of energy constantly form and burst. At these unimaginably tiny scales, the uncertainty principle reigns supreme, allowing energy to be borrowed from the vacuum for fleeting instants. This results in a frantic frothing of reality where virtual particle-antiparticle pairs spontaneously blink into existence and annihilate each other almost immediately. But it's far stranger than just particles. These fluctuations are so extreme that they warp the very geometry of spacetime itself, creating a foamy structure of tiny, transient wormholes and topological handles. A seething, probabilistic foam where the smooth continuum of spacetime shatters into a granular, chaotic dance. This isn't just theoretical speculation. It's a direct consequence of marrying quantum mechanics with general relativity. In our everyday experience, space and time appear smooth and continuous, like a perfectly flat sheet of glass. But if you could examine that glass under a microscope powerful enough, you'd see it's actually made of a granular, crystalline structure. Space-time foam is the ultimate version of this, the fundamental graininess of the universe. Here, the notions of a definite distance or a definite time interval lose all meaning. The foam is a probabilistic whirlwind where wormholes, tiny bridges connecting different points in spacetime, constantly form and collapse, and where the topology of space itself fluctuates wildly. It's a realm of pure quantum chaos, and the stunning proposal of this third secret is that the gravitational field we feel every day might not be a fundamental force at all, but rather the large-scale, statistical average of this microscopic chaos. Gravity, in this view, could be the cosmic equivalent of static noise, the background hiss you hear on a radio that is actually the sum of countless random electromagnetic signals. What we perceive as the steady, predictable pull of gravity could be the smoothed-out result of trillions upon trillions of quantum fluctuations in the foam, their random gravitational effects averaging out to produce the coherent force that structures our cosmos. The monumental challenge, of course, is finding a way to test this incredible idea. How do you probe a realm that is so tiny and so fleeting? This is where some of the most sensitive instruments ever built by humanity enter the story: gravitational wave observatories like LIGO and Virgo. These detectors have already opened a new window on the universe by listening to the ripples in spacetime caused by cataclysmic events like colliding black holes. But their incredible precision might also allow them to hear the faintest whispers of spacetime foam itself. The theory suggests that as a gravitational wave travels across billions of light years to reach us, its journey through this frothy, foamy quantum substrate might leave a subtle imprint on the wave. The chaotic foam could slightly scramble the waveform, adding a very specific kind of noise or jitter to the signal, a tiny deviation from the perfect ripple predicted by classical general relativity. Detecting this signature would be like hearing the faint crackle of static superimposed on a clear musical note, direct evidence that the wave has traveled through a grainy, quantum medium. Future observatories like the space-based LISA mission, or even more advanced telescopes, will be sensitive enough to listen for this cosmic static. Finding it wouldn't just confirm the foamy nature of spacetime, it would provide the first direct experimental evidence that gravity itself is born from the quantum realm, finally unifying the two great pillars of modern physics through the chaotic, beautiful noise of the vacuum. Now, we arrive at a secret that connects two of the most baffling concepts in all of physics, weaving them together into a single, elegant tapestry. This is the profound idea that the spooky, instantaneous connection of quantum entanglement might be the very glue that creates the force of gravity itself. To understand this, let's first revisit entanglement, a phenomenon so strange that even Einstein famously dismissed it as spooky action at a distance. Imagine two electrons are created together in a single event. According to quantum mechanics, their properties like spin become linked or entangled. No matter how far apart you separate them, across a lab or across a galaxy, measuring the spin of one electron will instantly determine the spin of the other. This connection seems to violate the cosmic speed limit set by the speed of light, and it suggests a layer of reality where information and correlation exist outside of our familiar spacetime. For decades, physicists treated entanglement and gravity as inhabitants of two completely separate worlds. Entanglement was the bizarre signature of the quantum realm, while gravity was the grand architect of the cosmos. But a groundbreaking conjecture, known as ER=EPR, has daringly proposed that these two worlds are not just connected. They might be one and the same. The conjecture, proposed by physicists Juan Maldacena and Leonard Susskind, links two ideas from Einstein's work that were previously thought to be unrelated. The ER refers to the Einstein-Rosen bridge, more commonly known as a wormhole, a theoretical tunnel through spacetime that could connect two distant points. The EPR refers to the Einstein, Podolsky, and Rosen paper that first highlighted the bizarre implications of quantum entanglement. The The conjecture stunningly proposes that these two concepts are equivalent. In other words, if two particles are entangled, they are not just spiritually connected. They are physically connected by a microscopic wormhole, a tiny bridge in the fabric of space-time itself. Let that sink in for a moment. The spooky action at a distance that so troubled Einstein might not be action across a distance at all. Instead, those two entangled particles could be linked by an ultra-tiny, Planck-scale shortcut through the universe, a wormhole. Their instantaneous correlation isn't a signal being sent. It's a reflection of their profound physical connectedness. This idea transforms our understanding of entanglement from a purely informational link into a geometric one, deeply woven into the structure of spacetime. This leads us to the breathtaking implication for gravity. If every pair of entangled particles is connected by a tiny wormhole, then what we perceive as the gravitational attraction between masses could actually be the collective effect of countless trillions of these microscopic bridges. A planet like Earth is made of an astronomical number of particles, and many of them are entangled with each other in a vast, complex web. This web of entanglement, manifested as a web of wormholes, could create the overall curvature of spacetime that we experience as gravity. In this view, gravity isn't a force being radiated or a dimple in a rubber sheet. It is the physical manifestation of quantum connectivity. The reason objects are drawn toward each other is not because they are pulling on some invisible field, but because they are already intimately linked through this hidden architecture of entanglement and wormholes. Every time you drop a pen and it falls to the floor, you might be witnessing the effects of a near infinite number of quantum threads, silently holding the universe together. This idea offers a stunningly beautiful and unified vision of reality. It merges the weirdness of the quantum world, where particles share a mysterious connection, with the grand structure of the cosmos, where gravity sculpts galaxies. It suggests that the quantum and the gravitational are not two separate languages but different dialects of a single, deeper truth. The fabric of the universe is not just threaded with fields and forces. It is stitched together by the invisible bonds of entanglement, and gravity is the emergent pattern we see when we step back to admire the entire cosmic tapestry. But this ceaseless quantum activity comes with an immense and puzzling price tag: energy. According to the most straightforward calculations in quantum field theory, the vacuum should be brimming with an unbelievable density of this vacuum energy. Every cubic centimeter of so-called empty space should contain more energy than all the matter in the entire observable universe. This isn't a small number. It's a value so catastrophically large that it defies any rational understanding of the cosmos we actually live in. If this calculated vacuum energy were real, its gravitational effect would be to curve spacetime so violently that the universe would have ripped itself apart moments after the Big Bang. Stars, planets, and life itself would be utterly impossible. And yet, here we are. This yawning chasm between theoretical prediction and observational reality is known as the cosmological constant problem, and it stands as perhaps the single worst discrepancy in all of theoretical physics. So where does this leave gravity? This is where the fifth secret offers a revolutionary shift in perspective. The prevailing assumption has been that this vacuum energy must act as a source for gravity, directly curving spacetime according to Einstein's equations. But what if that assumption is backwards? What if the secret isn't in finding a way to cancel out this immense energy, but in reinterpreting its very role? The emerging ideas from our 38 secrets suggest that vacuum energy might not be something that causes gravity, but rather something that is gravity. Instead of being a source that warps the stage, it might be the material from which the stage itself is built. In the entropic and emergent gravity theories we've discussed, the energy of the vacuum fluctuations could be what provides the microscopic degrees of freedom, the countless tiny moving parts whose collective behavior and tendency toward increasing entropy manifest as the force we call gravity. The vacuum energy isn't a problem to be solved, it's the essential ingredient. This radically changes how we approach the cosmological constant problem. The calculations that give an absurdly large value might be correct in a sense, but they are answering the wrong question. They are calculating the energy density as if it were a source within spacetime, when in fact, it might be the property that defines spacetime. The small, positive value of dark energy we observe the force accelerating the expansion of the universe might then be a kind of residual effect, a gentle pressure left over after the vast majority of the vacuum's energy has been spent on weaving the very fabric of reality itself. It's the difference between trying to calculate the weight of the ocean by weighing every single water molecule individually, an impossible task that gives a nonsensically large number, and instead recognizing that the ocean's true property is its fluidity, its pressure, and its waves. The secrets encoded in quantum fields are guiding us toward this profound realization. To understand gravity, we must stop seeing the vacuum as an empty container and start seeing it as the active, dynamic substance from which everything, including spacetime, emerges. Now, as we venture deeper into the quantum tapestry, we encounter a secret that offers one of the most elegant and mathematically beautiful solutions to the gravity problem, a concept known as supersymmetry. To understand its promise, we must first confront one of the most baffling questions in all of physics. Why is gravity so unimaginably weak? Consider the humble fridge magnet. With just a tiny piece of metal, you can effortlessly defy the gravitational pull of the entire Earth, a planet weighing over 6 sextillion tons. This isn't just a small difference in strength. The electromagnetic force is a staggering 100 undecillion times stronger than gravity. That's a 1 followed by 36 zeros. This monumental disparity is known as the hierarchy problem, and it screams that something fundamental is missing from our picture of the universe. Supersymmetry, often nicknamed SUSY, proposes a breathtakingly simple and symmetrical answer. It suggests that for every known fundamental particle in the universe, there exists a hidden super-partner particle. For every quark, there would be a squark. For every electron, a selectron. For every photon, a photino. This isn't just about doubling the number of particles for the sake of it. It's about restoring a profound balance to the laws of physics. In this supersymmetric world, the two great families of particles, the fermions that make up matter and the bosons that carry forces, are no longer separate clans. They become two sides of the same coin, connected through a deep and beautiful mathematical symmetry. A fermion can transform into its bosonic superpartner and vice versa, creating a cosmic dance of perfect partnership. So how does this elegant symmetry explain gravity's feebleness? The answer lies in the quantum corrections to the mass of the Higgs boson, the particle that gives all others their mass. In the Standard Model, these corrections are enormous, threatening to push the Higgs mass to scales 1 trillion times larger than it actually is. This is mathematically ugly and suggests our theory is incomplete. But in a supersymmetric universe, the superpartners step in to save the day. For every particle that contributes a large positive correction to the Higgs mass, its superpartner contributes an identical but negative correction. They are perfect canceling partners, gracefully keeping the Higgs mass, and by extension, the entire electroweak scale stable and small. This delicate cancellation doesn't just solve a technical problem. It explains why the scale of the atomic world and the scale of gravity are so different. Gravity appears weak because the other forces are effectively being protected and kept strong by this underlying supersymmetry. But the promise of SUSY extends far beyond just fixing a mass calculation. Its most profound implication is the potential to achieve the holy grail of physics, the unification of all forces. In our current Standard Model, the three quantum forces, electromagnetism, the strong nuclear force, and the weak nuclear force, are described by different quantum fields that seem distinct. However, when we mathematically project their strengths back to the unimaginably high energies of the Big Bang, their values almost, but not quite, converge at a single point. It's as if they were once a single, unified force that shattered as the universe cooled. Gravity, described by general relativity, stubbornly remains outside this circle, its strength on a completely different trajectory. This is where supersymmetry works its magic. When we add the contributions of all the proposed superpartners to these calculations, something miraculous happens. The lines representing the strength of all four fundamental forces, including gravity, bend and elegantly merge together at a single, monumental energy scale. This grand unification suggests that at the birth of the universe, there was no distinction between the force that holds atoms together and the force that holds galaxies together. There was only one unified superforce, mediated by the vibrations of a single master quantum field that incorporated all its superpartners. Supersymmetry provides the missing mathematical thread to weave gravity into the quantum tapestry, transforming it from an outsider into a key member of the family. The glaring caveat, of course, is that despite decades of searching, not a single superpartner particle has been found. Powerful atom smashers like the Large Hadron Collider have probed ever higher energies looking for a selectron or a squark, yet so far, the supersymmetric world remains hidden. This doesn't mean the idea is dead. It simply means that if supersymmetry is real, the superpartners are much heavier than initially hoped. They might only reveal themselves at energies far beyond our current reach, or they might be hiding in ways we haven't yet thought to look. For many theorists, the mathematical elegance and explanatory power of supersymmetry are too compelling to abandon. It remains a brilliant, unconfirmed melody in the symphony of the cosmos, a tantalizing secret whispered by the equations that could still hold the key to finally unifying Einstein's curved spacetime with the chaotic quantum realm. Now we arrive at a secret that asks us to expand our imagination beyond the three spatial dimensions we experience every day, venturing into the hidden folds of reality itself. String theory, one of the most ambitious frameworks in physics, proposes a truly breathtaking idea. The fundamental quantum fields that make up our universe don't just vibrate in the familiar length, width, and height we know. They also resonate in additional, unseen spatial dimensions, curled up into sizes so infinitesimally small that they have so far escaped all detection. And it is within this grand, multi-dimensional architecture that one of our greatest mysteries, the baffling weakness of gravity, might finally find its elegant explanation. To visualize how dimensions can be hidden, picture an ordinary garden hose stretched out across a lawn. From a great distance, it looks like a simple, one-dimensional line. An ant living on that hose would believe it could only move forward or backward. Its entire world would be that single dimension. But if we zoom in incredibly close, we see the hose's circular cross-section. That ant, if it were small enough, could actually travel in a second, tiny, curled-up dimension, circumnavigating the hose's circumference. Now, imagine that same principle applied to every single point in our three-dimensional space. According to string theory, there could be 6 or 7 additional spatial dimensions, but each one is curled up into a fantastically small, complex shape at a scale a billion times smaller than an atom. We don't perceive them not because they aren't there, but because they are too tiny for any instrument to probe. Our reality is like that garden hose. We are the ants blissfully unaware that at every location, there are entirely new directions to explore, if only we were small enough to see them. This radical idea provides a stunningly simple and elegant solution to the hierarchy problem, the immense gulf in strength between gravity and the other forces. The proposal is that while the electromagnetic, strong, and weak nuclear forces are generated by quantum fields that are confined to our familiar three-dimensional brain of existence, short for membrane, the gravitational field is different. It is not stuck here. It can propagate into all the extra, compactified dimensions. Think of our three-dimensional universe as a vast, thin sheet floating within a higher dimensional space. The other forces and all the particles of matter are like ink stains trapped on that sheet. They can't leave its surface, but gravity, the curvature of space-time, is like a drop of water that can soak through the entire paper towel, spreading out into the bulk of the higher dimensional space. This dilution is why gravity appears so weak to us. We are only feeling a tiny fraction of its true strength. The vast majority of its influence is leaking away into these unseen dimensions, its full power dissipated across a much larger volume of reality. In this framework, quantum fields play the role of cosmic architects and bridges. The fields that give rise to the particles of the Standard Model are like vibrations on the surface of a drumhead, producing notes we can hear. The gravitational field, however, is a vibration of the drumhead itself, and also of the air all around it. It is fundamentally connected to the geometry of the entire higher dimensional arena. This means that what we perceive as the humble force of gravity in our world is actually just the three-dimensional shadow of a far more powerful, multi-dimensional force. The quantum fields are the essential link, the translators that allow us to perceive the effects of these higher dimensional vibrations within our limited sensory palette. The implications of this are nothing short of revolutionary. It suggests that if we could ever probe these tiny, compactified dimensions, perhaps with a particle collider of unimaginable power, we might see gravity's strength suddenly increase or witness the appearance of exotic new particles corresponding to higher frequency vibrations of the strings in these extra dimensions. It paints a picture of a universe that is far vaster and more richly textured than we ever dreamed, with the force that holds our feet to the ground acting as our faint, but profound, connection to this magnificent hidden architecture. Gravity is no longer the odd force out. It is the only force giving us a whisper of the true, multi-dimensional nature of existence. But if gravity truly is a quantum force, woven from the same fabric as the others, then it too must have its own messenger particle, a carrier of the gravitational interaction. This brings us to the eighth secret, and one of the most sought-after phantoms in all of physics, the graviton. In the beautifully successful framework of quantum field theory, every fundamental force is mediated by a specific type of particle that acts as its carrier. The electromagnetic force is conveyed by photons, packets of light energy that are exchanged between charged particles. The strong nuclear force, which holds atomic nuclei together, is carried by gluons. The weak nuclear force operates through the exchange of W and Z bosons. This particle exchange mechanism is the very heart of how forces work in the quantum realm. It's how particles feel each other's influence. It's a cosmic game of catch on an unimaginably tiny scale. Following this elegant pattern, the graviton is the hypothetical particle proposed to be the quantum carrier of the gravitational force. Just as a photon is a discrete packet of energy that represents the smallest possible excitation of the electromagnetic field, a graviton would be the smallest possible ripple, the fundamental quantum of the gravitational field. If we could listen to the symphony of space-time, the individual notes would be gravitons. This idea is more than just an analogy. It's a mathematical necessity if we want gravity to fit into the same quantum framework as every other force. The existence of the graviton is the definitive prediction of any theory that successfully quantizes gravity. Finding it would be the ultimate smoking gun, the irrefutable proof that gravity is, at its core, a quantum phenomenon. So what would a graviton look like, and why has it proven so impossibly elusive? Based on the properties of gravity as we understand it from general relativity, physicists can deduce the necessary characteristics of its quantum carrier. The graviton must be a massless particle, just like the photon, because gravity has an infinite range stretching across the entire cosmos. It must travel at the speed of light, the the universe's ultimate speed limit. And crucially, it must have a quantum spin of 2. This last property is what truly sets it apart. A photon has a spin of 1. An electron has a spin of 1/2. A spin 2 particle is something entirely different and is uniquely suited to describe the geometry of spacetime itself. This is because the gravitational field isn't just a field in spacetime. According to Einstein, it is spacetime. The graviton wouldn't just be another particle moving on the stage. It would be a tiny vibration of the stage. This profound difference is the root cause of our immense difficulty in detecting it. The challenge of finding a graviton is almost incomprehensibly greater than detecting any other particle. The reason lies in gravity's incredible weakness. The feebleness of the gravitational force means that the interaction between individual gravitons and matter is vanishingly small. To put it in perspective, a gravitational wave detector like LIGO, which can sense ripples in spacetime from colliding black holes billions of light-years away, requires an energy flux of around 100 watts per square meter to produce a measurable signal. That wave is composed of a staggering number of gravitons. To have even a 50-50 chance of detecting a single graviton with a similar instrument, you would need a detector with the mass of Jupiter. And you would have to wait for a time longer than the current age of the universe. It's a sobering calculation that suggests direct detection of a lone graviton with traditional methods may forever be beyond our reach. Yet, the human drive to discover is undeterred, and physicists are pursuing ingenious, indirect avenues to confirm the graviton's existence. One of the most promising frontiers involves not colossal detectors, but some of the coldest objects in the known universe, Bose-Einstein condensates. These are exotic states of matter where a cloud of atoms is cooled to a fraction of a degree above absolute zero. At these temperatures, the atoms lose their individual identities and merge into a single, coherent quantum entity, behaving like one giant wave. This ultra-sensitive state makes them perfect laboratories for probing the most subtle quantum effects. The groundbreaking idea is to use such a condensate to try and detect the faint, specific noise that would be generated by gravitons. Just as photons can exert a tiny pressure of light, gravitons should exert an even tinier gravitational pressure. By meticulously monitoring the impossibly small jiggling of atoms within a Bose-Einstein condensate, scientists hope to identify a signature pattern, a specific spectrum of quantum noise, that could only be caused by the sea of virtual gravitons constantly flashing in and out of existence in the vacuum around it. It would be like listening for the faint, collective hum of the gravitational field itself. Success in such an experiment wouldn't show us a single graviton, but it would provide overwhelming evidence for their existence as the fundamental excitations of the quantum gravitational field, finally weaving the last force into the quantum tapestry. While string theory adds extra dimensions to the fabric of reality, another profound approach to unifying gravity and quantum mechanics takes a completely different path, suggesting that the problem isn't the number of dimensions but the very nature of space itself. This is the ninth secret, the revolutionary idea from loop quantum gravity that space is not a smooth, continuous fabric, as Einstein described, but is instead granular, woven from indivisible, finite loops, a cosmic tapestry with a fundamental pixel size. Imagine zooming in on a digital photograph on your screen. From a distance, the image appears smooth and continuous, with gentle gradients and curves. But as you zoom in closer and closer, you eventually see the individual pixels that make up the entire picture. You reach a point where you cannot zoom in any further. You've hit the fundamental resolution of the image. Loop quantum gravity proposes that the universe operates on exactly this principle. There is a smallest possible unit of space, a tiny quantum of volume, a single pixel of reality itself. In this theory, space is not a passive stage on which particles move. It is a dynamic, physical substance made of a network of intersecting loops. Think of it as an unimaginably fine mesh, or a spider's web of one-dimensional lines, where each tiny loop carries a specific quantum of area. The intersections of these loops, called nodes, represent the tiniest possible volumes of space. The entire universe, every empty void, every planet, every galaxy, is this evolving, vibrating network of loops. What we perceive as the smooth, three-dimensional world around us is the large-scale average of this frenetic, granular underlying structure. Much like a woven piece of cloth appears smooth from a distance despite being made of individual threads. In this framework, the quantum fields we've discussed, like the electron field or the electromagnetic field, are not in space. They live on this network of loops. Their excitations are tied to the geometry of the loops themselves, making matter and geometry inseparable partners from the very beginning. This leads to the most powerful aspect of this idea. It is a background-independent theory. In most of physics, including the Standard Model and even string theory, quantum fields are defined on a pre-existing, smooth spacetime background. It's the stage that's already there before the actors appear. But loop quantum gravity eliminates this stage. There is no spacetime until the loops themselves weave it into existence through their interactions and relationships. Gravity isn't a force propagating through space. It is the direct manifestation of the changing geometry of this loop network. The attraction between two masses is the result of the way the loops connecting them evolve and interact, changing the quantum state of the geometry between them. This makes loop quantum gravity a truly relational theory. Space and time only have meaning in terms of how the loops connect to each other, offering a profoundly different philosophical starting point for understanding the cosmos. The most stunning consequences of this discrete view of space emerge in the most extreme environments in the universe, the centers of black holes and the very beginning of the Big Bang. In Einstein's general relativity, these are points of infinite density and curvature called singularities, where the laws of physics completely break down and our equations spit out meaningless infinities. They are arguably the most powerful signals that our theory is incomplete. Loop quantum gravity naturally resolves this catastrophe. Because space is granular, you simply cannot compress matter and energy into an infinitely small point. It would be like trying to force more and more data into a single pixel on your screen. Eventually, you hit a hard limit. As matter collapses under its own gravity to form a black hole, or as the universe is compressed backwards in time toward the Big Bang, the repulsive force arising from the discrete quantum geometry becomes enormous. Instead of collapsing to a point of zero volume, the collapsing matter hits a point of maximum possible density and then rebounds. This means there is no singularity at the heart of a black hole. Instead, the collapsing star would reach a tiny, finite size and then explode outward into a new region of spacetime, effectively becoming a white hole, a region where matter and energy are expelled. Our universe might not have begun from a single, infinitely dense point, but from a great bounce, the recoil of a previous universe that had contracted to its minimum possible size. This breathtaking idea replaces the terrifying, physics-breaking singularity with a quantum bridge to another spacetime, turning cosmic endpoints into portals. The fabric of spacetime, woven from finite loops, cannot be torn into infinities. It can only be stretched and compressed within its fundamental limits, forever preserving the laws of physics and offering a vision of the cosmos that is potentially eternal and cyclical. This brings us to one of the most profound and long-standing puzzles in all of theoretical physics, a problem that has pitted the two great pillars of our understanding against each other for decades: the black hole information paradox. At its heart, this paradox strikes at a fundamental tenet of quantum mechanics, the principle that information is never truly lost. In the quantum world, if you know the complete current state of a system, you should, in principle, be able to calculate its entire past and future. Every interaction, every collision, every decay is reversible in the sense that the information about what went in is always preserved in what comes out. You can burn a book, and while it may seem the information is gone, a hypothetical super-intelligent being could, from the precise state of the smoke and ashes, reconstruct every single word. Information in quantum theory is forever. Then along came Stephen Hawking, who made a startling discovery in the 1970s. He realized that black holes are not completely black. Due to intense quantum effects right at the edge of their event horizons, they slowly and steadily radiate energy. This Hawking radiation is thermal. It has the character of random heat, like the glow from a hot piece of coal. And herein lies the catastrophe. As a black hole emits this radiation, it slowly loses mass and eventually evaporates completely, disappearing from the universe. The problem is that the Hawking radiation appears to be purely random, carrying no specific information about the particular star, spaceship, or book that originally fell in. If you toss a unique, leather-bound encyclopedia into a black hole, the radiation that eventually comes out seems to be identical to the radiation you'd get from tossing in a scrambled pile of garbage. When the black hole is gone, all that remains is this formless thermal radiation. The specific, quantum information about the encyclopedia appears to have been erased from the universe, violating a sacred rule of quantum mechanics. It's as if the universe itself has a giant shredder. And this paradox suggested that our most fundamental laws of physics are fundamentally inconsistent when gravity gets involved. For decades, this was the status quo. A stalemate between the immutable laws of quantum information and the inexorable gravity of black holes. But the 10th secret we explore today offers a breathtaking and elegant resolution, one that comes directly from the behavior of quantum fields themselves. The key insight is that the information isn't actually lost inside the black hole. It never made it past the point of no return in the first place. Instead, the subtle, intricate correlations within the quantum fields that are constantly fluctuating just outside the event horizon act as a cosmic backup drive. As particles are created in the Hawking radiation process, their partners that fall into the black hole are not independent. They are intricately linked or entangled with the radiation that escapes. These entangled connections are not just simple pairs. They form a fantastically complex web of correlations that subtly encode the information about everything that has ever fallen into the black hole. The information isn't burned. It's imprinted onto the structure of the Hawking radiation itself, in a way that is so delicate and spread out that it looks like random noise to anyone who doesn't know how to decode it. It's like a master painter dissolving their masterpiece into a seemingly random cloud of colored mist. The information of the painting is still there, but you need the right recipe to condense the mist back into the image. This is where a recent and powerful advance, known as the island formula, enters the story, providing the mathematical mechanism for how this information preservation actually works. The formula comes from applying the holographic principle and tools from quantum information theory to black holes. It reveals that when we calculate the total information content, or entropy, of the Hawking radiation leaving a black hole, we must include not just the radiation far away, but also a mysterious, disconnected region that appears in the calculation. A region dubbed the island. This island isn't a physical place you could travel to. It's a region of space-time that emerges in the mathematics, and it sits just inside the event horizon of the black hole. Astonishingly, this mathematical construct implies that the information we thought was trapped deep inside the black hole is actually physically connected to the radiation outside through the weirdness of quantum entanglement. The island acts as a quantum bridge, allowing the information to be simultaneously inside and outside the black hole, ensuring it is never truly lost. As the black hole evaporates, This island grows, effectively pulling the information back out and transferring it into the escaping radiation. In the final moments of the black hole's life, the last bits of radiation are not random at all. They contain the precise, recovered information of the first things that fell in. The cosmic shredder has been revealed to be the most sophisticated filing system imaginable. The profound implication of this resolution is that it forces gravity to play by the rules of quantum mechanics. The paradox wasn't a sign that quantum theory was wrong, but that our classical understanding of gravity was incomplete. By showing how quantum fields at the horizon preserve information through entanglement and subtle correlations, we see that gravity, in its most extreme manifestation, must fundamentally respect the quantum principle of unitarity, the conservation of information. This doesn't just solve a 40-year-old puzzle. It forges a crucial link in the chain unifying these two worlds. It demonstrates that the fabric of space-time and the quantum fields that live upon it are not just interacting. They are so deeply intertwined that one cannot exist without the other. The event horizon of a black hole is not a wall of death, but a laboratory of creation, where the dance of quantum fields writes the story of everything that enters into the very radiation that seems to erase it, proving that in the universe, nothing is ever truly forgotten. For centuries, cosmologists envisioned a universe slowing down under the relentless pull of gravity, a grand cosmic deceleration leading to either a big crunch or a slow, cold fade. But at the turn of the millennium, observations of distant supernova delivered a shocking plot twist. The universe isn't slowing down at all. It is accelerating, flying apart at an ever-increasing rate, as if some mysterious, repulsive force is stretching the very fabric of spacetime itself. This mysterious driver of cosmic acceleration was dubbed dark energy, and it constitutes the single largest component of the universe, a staggering 68% of all that exists. Yet, its true nature remains one of the greatest enigmas in all of science. The 11th secret we explore proposes a breathtaking solution, suggesting that dark energy is not some alien, external force, but a dynamic effect emerging from a specific type of quantum field, a field known as quintessence. The simplest explanation for dark energy, and the one currently favored by the standard model of cosmology, is Einstein's cosmological constant, a fixed, immutable energy density inherent to the vacuum of space itself. It acts as a constant push, a kind of anti-gravity that becomes dominant as the universe expands and matter dilutes. But this simple idea comes with profound problems. The calculated value of this vacuum energy from quantum field theory is astronomically larger than the tiny value we observe, a discrepancy of about 120 orders of magnitude, the worst prediction in the history of physics. This colossal failure suggests that the cosmological constant might be the wrong answer, or at least an incomplete one. This is where quintessence enters the stage, offering a far more dynamic and intriguing alternative. Quintessence, named after the classical fifth element believed to fill the heavens, is theorized to be a quantum field that permeates all of space, much like the Higgs field. But unlike the Higgs, which gives particles their mass, or the electromagnetic field, which gives us light, the quintessence field would have a unique and peculiar property, a negative pressure. Imagine a vast, invisible fluid filling the cosmos. If this fluid had a strong negative pressure, it would act counterintuitively. Instead of resisting being stretched, it would actually do the opposite. Stretching it would add energy to it. As the universe expands, stretching the fabric of space-time, this quintessence field gains energy, and that gained energy manifests as a repulsive gravitational force that drives the expansion to accelerate even faster. It's a self-reinforcing cycle. Expansion feeds the field, and the field drives more expansion. In this view, dark energy isn't a constant but a dynamic, evolving phenomenon, its strength potentially changing over the deep time of the cosmos. This idea creates a profound and elegant link between the largest and smallest scales of reality. If both dark energy and gravity are manifestations of quantum field dynamics, then the entire fate of the cosmos, from the acceleration of galaxies to the curvature of space-time, is governed by the principles of quantum physics. The gravitational attraction we feel and the cosmic repulsion we observe are not two separate, warring forces. They are two different outcomes of the same underlying quantum mechanical processes. Gravity, as we've explored in previous secrets, may emerge from the entanglement and information of quantum fields. Dark energy, as quintessence, would be the large-scale effect of a specific quantum field's negative pressure. This paints a unified picture where the quantum world doesn't just explain the tiny realm of particles. It literally holds the blueprint for the evolution, structure, and ultimate destiny of the entire universe. The force that determines whether the cosmos ends in a fiery crunch or an eternal, silent freeze is not written in the stars, but in the fluctuating, probabilistic nature of the quantum fields from which everything, even space-time itself, emerges. This profound mystery of gravity's incredible weakness, a force dwarfed by even the most mundane magnet, leads us to a secret that is as much about philosophy as it is about physics. It compels us to ask not just how gravity is so weak, but why it is precisely as weak as it is. Could the answer lie not in a fundamental law, but in the simple, staggering fact that we are here to ask the question? This is the core of the Anthropic Principle, a concept that suggests the constants of nature, including the strength of gravity, might be what they are because only in a universe with these specific values could conscious, questioning life like us ever evolve to observe them. To grasp this idea, let's step away from the cosmos for a moment and consider a much simpler analogy: a puddle of water. After a rainstorm, a puddle forms in a small depression on the ground. The water perfectly conforms to the shape of the hole. The puddle might look at itself and marvel, how astonishing it is that this hole in the ground is shaped so perfectly to hold me. It fits my form exactly. It must have been designed just for me. But of course, that's the wrong way around. The hole wasn't made for the puddle. The puddle simply formed in a hole that happened to be there. In the same way, we find ourselves in a universe whose fundamental constants, like the gravitational constant, seem perfectly tuned for life. The Anthropic Principle flips the reasoning. The universe wasn't necessarily designed for us. Rather, we are a product of a universe that had the right conditions to allow our existence. In a universe where gravity was even slightly stronger or weaker, the story of life might never have been written. This line of thinking finds its most powerful expression in the concept of the multiverse, a vast, perhaps infinite, ensemble of universes, each with its own unique set of physical laws and constants. In this breathtaking cosmic landscape, the quantum fields that underpin reality could take on different properties in each separate universe. In some universes, the fields responsible for electromagnetism might be weaker. In others, the Higgs field might give particles far more mass. And crucially, in many, perhaps even most of these universes, the gravitational constant could be radically different. Some might have gravity so strong that any universe that forms would immediately collapse back into a black hole before a single star could ignite. Others might have gravity so weak that matter could never coalesce into galaxies, stars, or planets, remaining forever as a thin, sterile mist of gas and dust. In this vast multiversal lottery, only a tiny, fortunate sliver of universes would have the exact right, Goldilocks combination of constants, a gravitational strength that is just right, to allow for the formation of complex structures and, eventually, life. We, quite obviously, find ourselves in one of those rare, bio-friendly universes. This perspective doesn't provide a neat mathematical formula for why the gravitational constant has the value it does, but it offers a profound philosophical resolution to the puzzle of fine-tuning. The weakness of gravity is not a bizarre anomaly waiting for a deeper quantum field explanation. It might simply be a necessary condition for our existence. The specific properties of the quantum fields in our universe, their symmetries, their coupling strengths, the way they interact to produce the effective force of gravity, are the winning numbers in a cosmic lottery. They are the values that allowed for a universe with long-lived stars, stable planetary orbits, and the complex chemistry that leads to living, breathing, curious creatures who can look up at the night sky and wonder about the force that holds their world together. It is a humbling and expansive idea that places our entire physical reality within a much grander, and perhaps more random, context. Now we venture into a secret that asks us to consider not just the energy or vibrations of quantum fields, but their very shape. The intricate and persistent twists and knots that might be woven into the fabric of reality itself. This is the profound idea that the topology of quantum fields could be the hidden architect of gravity, a concept that merges the abstract mathematics of shape with the tangible force that holds the cosmos together. Topology is the branch of mathematics concerned with properties that remain unchanged when an object is stretched, twisted, or bent, but not torn. A coffee mug and a donut are topologically identical to a mathematician because one can be smoothly deformed into the other. They both have exactly one whole. This secret proposes that quantum fields themselves can possess such topological features, not just temporary fluctuations, but stable, knotted configurations that are incredibly difficult to undo. These aren't mere wrinkles in the field. They are fundamental, particle-like structures known as topological defects, and they might hold the key to some of gravity's deepest mysteries. Imagine a vast, abstract field filling all of space, much like the Higgs field that gives particles mass. Now, picture this field not as a perfectly flat, uniform sheet, but as a complex, multi-dimensional tapestry. In some regions, the values of this field might form closed loops, knots, or other non-trivial structures. Due to the field's specific properties, these knots can be incredibly stable, persisting for eons almost as if they were tangible objects. A famous and elegant analogy is the cosmic string, a hypothetical one-dimensional topological defect that might have formed in the early universe as it cooled. Think of it like ice forming on a pond. As the water freezes, cracks and fissures can appear, regions where the crystalline structure doesn't align perfectly. A cosmic string would be a similar crack in the quantum fields that fill the universe, an incredibly thin, unimaginably dense filament of energy, 1 billion times thinner than a proton, but with the mass of a mountain range per centimeter. The gravitational influence of such an object would be immense, warping space-time around it in dramatic ways. This is where the connection to gravity becomes breathtakingly direct. The immense energy density contained within these knotted field configurations would, according to Einstein's equations, curve the surrounding space-time. A network of such cosmic strings left over from the Big Bang could create a cosmic web of gravitational anomalies, but the implications go even further. Some theoretical models suggest that what we perceive as dark matter, the invisible substance whose gravitational pull shapes galaxies, might not be a cloud of unknown particles at all. Instead, it could be the collective gravitational effect of a vast number of these topological defects. A galaxy might be filled with a froth of knotted quantum fields, their combined mass warping the orbits of stars without emitting a single particle of light. This offers a geometric interpretation of a force. Gravity isn't something applied to these knots. It is the inherent and unavoidable consequence of their twisted, energetic shape embedded within the fabric of reality. The force that guides the motion of galaxies could be the silent echo of the universe's topological imperfections, frozen into place during its fiery birth. But if entanglement weaves a hidden web of connection, Then the next secret reveals that this web might operate in a way that defies our most fundamental notions of time and space, suggesting that gravity itself could be an inherently non-local phenomenon. To understand this, we must first grapple with one of the most mind-bending aspects of quantum mechanics, non-locality. In our everyday classical world, if you want to influence something, you have to touch it or send a signal to it. A push, a sound wave, a beam of light. Everything is local, meaning cause and effect are limited by the speed at which information can travel. But the quantum world operates under a completely different set of rules. When two particles become entangled, as we've seen, a measurement on one seems to instantly influence the state of the other, no matter the distance separating them. This spooky action at a distance, as Einstein called it, demonstrates that quantum fields are fundamentally non-local. Their connections and correlations exist outside the familiar confines of space-time, suggesting a deeper, more interconnected layer of reality. Now, if gravity is indeed emergent from the quantum realm, as so many of our secrets suggest, then it stands to reason that it might inherit this bizarre property of non-locality. This would mean that gravitational interactions could, in some way, also transcend the limitations of space and time. The gravitational influence of an object might not be confined to propagating outward at the finite speed of light, rippling through space-time as a wave. Instead, there could be an instantaneous, non-local component to gravity, a connection that operates through the same hidden quantum channels that link entangled particles. This isn't to say that if the sun suddenly vanished, we would instantly float off into space. The structure of spacetime itself would still need to readjust, likely at the speed of light. But on a deeper, quantum gravitational level, the information about that change might be communicated non-locally through the entangled fabric of the universe, a silent hum of connection that bypasses normal channels. This radical idea offers a stunningly elegant solution to one of cosmology's most persistent puzzles, the horizon problem. When we look out at the cosmic microwave background radiation, the faint afterglow of the Big Bang, we see a universe that is incredibly uniform. The temperature of this radiation is the same in all directions to within 1 part in 100,000. This presents a profound mystery. According to the standard Big Bang model, these distant regions of the early universe were too far apart to have ever been in causal contact. Light, and therefore any information about temperature, would not have had enough time since the beginning of the universe to travel between them. It's as if you walked into a vast concert hall and found thousands of people who had never met all humming the same note in perfect pitch, with no conductor and no way to have communicated. How did these disconnected regions coordinate themselves so perfectly? Inflationary theory, which proposes a period of ultra-rapid expansion just after the Big Bang, is the mainstream solution, stretching a tiny, uniform patch to become our entire observable universe. But non-local gravity offers a fascinating alternative. If gravitational interactions were non-local in the early universe, then these distant regions didn't need to exchange light signals to come into equilibrium. They were already connected from the very beginning through the non-local web of quantum gravity. The universe wasn't born as a collection of disconnected points. It was born as a single, entangled whole. This primordial non-locality would have allowed for instant communication and thermalization, ensuring a uniform temperature everywhere. The horizon problem ceases to be a problem because there never was a true horizon separating these regions. They were always in contact, not through spacetime, but through the deeper quantum substrate from which spacetime itself emerges. This perspective paints a picture of a cosmos that is fundamentally unified, with non-local gravity acting as the ultimate cosmic glue that bound everything together in its first moments. A connection so profound it set the stage for the large, smooth universe we inhabit today. Now we come to one of the most powerful and paradigm-shifting ideas in all of modern theoretical physics. a concept so profound it has reshaped how we think about reality itself. This is the AD-S/CFT correspondence, a groundbreaking duality that acts as a kind of universal translator between two seemingly incompatible worlds, the world of gravity and the world of quantum particles. At its heart, this secret proposes an astonishing equivalence. A theory of gravity operating in a particular kind of warped space is completely and utterly equivalent to a special type of quantum field theory that operates on the boundary of that space, a theory that has no gravity in it at all. It's a revelation that suggests the force that shapes the cosmos might be a holographic projection, a cosmic shadow play encoded on a lower dimensional screen. To grasp this, we first need to understand the two halves of this incredible duality. The AD-S part stands for anti-de Sitter space. This is a hypothetical universe with a very specific and somewhat strange geometry. Unlike our own universe, which is expanding at an accelerating rate, an anti-de Sitter universe is negatively curved, like the surface of a saddle, and it has a boundary, a kind of outer edge or shell at an infinite distance. It's within this bulk volume that a full theory of quantum gravity, complete with black holes, strings, and the warping of space-time, is presumed to operate. The CFT part stands for conformal field theory. This is a particular type of quantum field theory that lives on the boundary of that anti-de Sitter space. This theory describes the interactions of particles and fields, but it is a theory without any gravity whatsoever. The miraculous claim of the correspondence is that these two theories, one with gravity in a higher dimensional bulk and one without gravity on a lower dimensional boundary, are two completely equivalent descriptions of the exact same physical reality. They are different languages telling the exact same story. A simple, everyday analogy can help illuminate this mind-bending concept. Imagine a vast, silent, and perfectly still swimming pool. This pool represents our anti-de Sitter space. Now, imagine that on the surface of this pool, there is a very thin, invisible film of oil. This oil film is our conformal field theory. It's a two-dimensional world existing on the boundary of the three-dimensional pool. If you were to tap the water in the pool, you would create ripples complex, three-dimensional waves that move through the depth of the water. These ripples represent events in the gravitational theory, the collision of particles, the formation of black holes, the curvature of space-time. Now, shift your perspective to the oil film on the surface. The movements and interactions of the molecules within that oil film would perfectly mirror and encode the information about those three-dimensional ripples. By studying the complex dynamics of the two-dimensional oil slick, a world with no concept of depth, you could, in principle, completely reconstruct every detail of the three-dimensional waves beneath it. The gravity in the bulk is not just related to the quantum fields on the boundary, it is encoded by them. The three-dimensional world is a holographic projection of the two-dimensional data. This correspondence, first proposed by physicist Juan Maldacena in 1997, is far more than a mathematical curiosity. It is an incredibly powerful tool. For decades, physicists have struggled to understand the quantum nature of gravity because the mathematics involved is notoriously difficult, often yielding nonsensical infinities. However, the mathematics of certain quantum field theories, especially those without gravity, is much more manageable. The AD-S/CFT correspondence provides a backdoor. A physicist wanting to solve an impossibly hard problem about what happens inside a black hole in the gravitational bulk can instead translate or map that problem onto a much more tractable problem involving the quantum fields on the boundary. It's like trying to understand the intricate workings of a massive, complicated engine by instead studying the detailed instruction manual written for it. The manual is a completely different object, made of paper and ink instead of steel and pistons, but it contains all the information needed to describe the engine perfectly. In this way, the AD-S/CFT duality has become a workhorse for theoretical physicists, allowing them to use well-understood quantum field theories to make startling discoveries about quantum gravity, black hole thermodynamics, and the very nature of space-time. The most profound implication of this secret is that it provides the strongest mathematical evidence yet for the holographic principle we discussed earlier. Our own universe might not be an anti-de Sitter space. In fact, evidence suggests it's not, but the success of this correspondence strongly hints that a similar holographic description could be true for us. It suggests that all the information that describes our seemingly three-dimensional world, with its rich gravitational phenomena, might be entirely encoded on a distant, two-dimensional surface at the edge of the cosmos. The force of gravity, in this view, is not something that exists in addition to the quantum fields. It is the emergent manifestation of how that lower-dimensional information is organized and processed. The AD-S/CFT correspondence is the Rosetta Stone that is finally allowing us to read the cosmic code, showing us that the quantum and the gravitational are not two separate realities, but two different perspectives on a single, unified truth. Yet even Einstein's masterpiece, the magnificent equations of general relativity that describe the cosmic dance of spacetime, is not the final word. It is a classical theory, a symphony of smooth geometry that plays perfectly across the vast scales of the universe but falls silent when the chaotic, probabilistic music of the quantum world begins. This profound limitation brings us to our 16th secret, a crucial step in our quest for unification: the idea that quantum fields themselves might provide the necessary corrections to Einstein's equations, adding subtle new notes to the symphony that only reveal themselves in the most extreme environments. To understand why such corrections are not just likely but absolutely necessary, we must revisit the central conflict. General relativity portrays spacetime as a smooth, continuous fabric that curves in a deterministic way in response to matter and energy. But as we've journeyed through these secrets, we've seen that the quantum vacuum is anything but smooth and peaceful. It is a seething, turbulent sea of virtual particles constantly flashing in and out of existence. According to quantum field theory, this relentless activity must contribute to the energy content of the universe. And since energy, according to Einstein, curves spacetime, this vacuum energy should gravitate. It should act as a source term in the equations of general relativity. But when physicists perform this calculation, the result is a number so absurdly large, it would have caused the universe to curl up into a tiny ball instantly after the Big Bang. This cosmological constant problem is the loudest and clearest signal that our classical theory of gravity is incomplete. It is utterly blind to the quantum world, and for the equations to make sense, they must be updated or renormalized with terms that account for these quantum effects. These necessary updates are what physicists call quantum corrections. The primary mechanism through which they arise is the concept of virtual particle loops. Imagine the gravitational field between two masses, like the Sun and the Earth. In the classical view, this is a smooth, curved groove. But in the quantum view, that empty space between them is teeming with activity. Virtual particle-antiparticle pairs are constantly emerging from the vacuum, existing for a fleeting moment before annihilating each other. These ephemeral particles can interact with the gravitational field itself, effectively screening or amplifying the force in incredibly subtle ways. It's as if the smooth groove of spacetime is actually filled with a fine, buzzing mist that slightly modifies how objects roll along it. Calculating the effect of all possible particle loops leads to new terms that must be added to Einstein's equations, terms that represent the back reaction of the quantum vacuum on the geometry of spacetime itself. These corrections are vanishingly small under normal conditions, which is why general relativity works so flawlessly for predicting planetary orbits and gravitational lenses. But in regimes of immense gravity or tiny scales, they become paramount, potentially resolving the infinities that plague our current theories. One of the most exciting places to look for the fingerprints of these quantum corrections is at the edge of a black hole, specifically in the nature of Hawking radiation. Stephen Hawking's original calculation treated the quantum fields producing the radiation as happening on a fixed, classical black hole background. But this is an approximation. In a more complete treatment, the radiation itself carries away energy, causing the black hole to shrink, which in turn slightly alters the gravitational field from which more radiation is emitted. This feedback loop is a quantum gravitational effect. When physicists begin to incorporate these corrections, the story of how a black hole evaporates and whether information is lost can change dramatically. The purely thermal, information-free radiation of the original calculation might gain subtle correlations, tiny deviations from perfect blackbody spectrum that could preserve the information of what fell in. The event horizon itself might develop a complex quantum fuzzy structure, often called a quantum atmosphere, rather than being a perfectly sharp boundary. Probing this with future generations of gravitational wave telescopes could provide our first indirect evidence of these quantum corrections at work. On the very largest of scales, the scale of the entire cosmos, quantum corrections could hold the key to understanding our universe's deepest mysteries: dark energy and the initial singularity. The cosmological constant, that enigmatic driver of cosmic acceleration, might not be a true constant at all. The quantum corrections from evolving fields could make it a dynamic entity, a value that has changed over the 14-billion-year history of the universe. This idea, known as quintessence, is a direct result of considering such corrections. Furthermore, the terrifying singularity at the beginning of time, a point of infinite density where general relativity breaks down completely, might be completely avoided. Quantum corrections are expected to become so strong at such enormous densities that they would effectively act as a repulsive force, preventing the collapse to a true singularity, and instead suggesting a bounce from a previous universe or a smooth quantum beginning. The entire fate of the cosmos, from its birth to its death, may be dictated by these subtle quantum whispers encoded in the fields that fill the void. The grand challenge, of course, is moving from theoretical elegance to experimental confirmation. How do you test effects that are ordinarily a billion times too small to measure? The answer lies in seeking out nature's most extreme gravitational laboratories. The collisions of black holes and neutron stars, observed through gravitational waves, are one such arena. The precise shape of the gravitational wave signal, its ringing as the final black hole settles down into a quiet state, is exquisitely sensitive to the properties of spacetime around the event horizon. Any deviation from the predictions of pure general relativity in this ring-down phase could be the signature of quantum corrections at work. Another frontier is the study of the cosmic microwave background radiation, the faint afterglow of the Big Bang. The patterns imprinted in this ancient light are a fossil record of the universe's infancy, a time when quantum gravitational effects were potentially dominant. Meticulously mapping the polarization and temperature fluctuations of this radiation with next-generation space telescopes could reveal statistical anomalies that point directly to the quantum corrections that shaped the cosmos in its first fleeting moments. Each of these observations is a potential window, a chance to peer beyond Einstein's classical masterpiece and catch a glimpse of the deeper, quantum-corrected theory that must surely lie beyond. Now, we delve into a secret that reveals a profound and beautiful pattern running through the very heart of physics, a pattern of symmetry, and more importantly, the breaking of that symmetry, which may be the very mechanism that gave gravity its unique and feeble character. To understand this, we must first appreciate the power of symmetry in nature. In physics, a symmetry isn't just about something looking the same on both sides. It's a fundamental property that remains unchanged under a transformation, like rotating a sphere or moving through empty space. These symmetries are the bedrock of our laws of physics, dictating the conservation of energy, momentum, and charge. They are the reason the universe operates with such elegant consistency. But the universe as we experience it is not perfectly symmetrical. If it were, all fundamental particles would be massless, zipping around at the speed of light, and the rich structure of atoms, molecules, and people would be impossible. This is where the magic of spontaneous symmetry breaking comes in. Imagine a perfectly round, spherical pencil balanced on its tip. This setup has a high degree of symmetry. You can rotate it any way you like and it looks the same. But this state is unstable. The slightest breath of air will cause it to fall over and land on its side, pointing in one specific, random direction. The symmetry of the system has been broken. It is no longer the same from every angle. Yet, this broken state is where the pencil finds its stability. In a very similar way, the quantum fields that fill our universe can exist in a highly symmetric but unstable state. As the hot, dense early universe cooled, these fields fell over, settling into a stable state that broke their original perfect symmetry. The most famous example of this is the Higgs field. In its symmetric state, it would give no particles mass. But as the universe cooled, it settled into a non-zero value everywhere, like a faint, invisible molasses that slows down certain particles, giving them the property we call mass through the now famous Higgs mechanism. This breathtakingly powerful idea, which earned a Nobel Prize, might not be confined to the realm of particles. It could be the very key that unlocks the mystery of gravity's nature. Just as the Higgs mechanism breaks symmetry to give mass to particles, gravity itself might be the result of a similar cosmic breaking of symmetry, but on a far grander scale. Some of the most compelling theories for a theory of everything, such as certain grand unified theories, begin with a reality that possesses a magnificent, higher dimensional symmetry. In this pristine state, all forces, electromagnetism, the nuclear forces, and gravity, are unified into a single master force, described by a single, supremely symmetric field. There is no distinction between them, they are all one. But as this higher dimensional universe expanded and cooled, it underwent a series of phase transitions, much like water freezing into ice. With each transition, a symmetry was broken. In one such break, the force of gravity may have been spun off from the others. The specific idea is that the original, symmetric field included a particle that would become the graviton, the hypothetical carrier of gravity. But during symmetry breaking, this graviton could have acquired a tiny mass, or perhaps other properties that fundamentally altered how it interacts. In many particle physics models, a force carrier with mass has a much shorter range than a massless one. This could explain why gravity is so weak compared to the other forces. Its carrier might not be completely massless, giving it an extremely limited range at the quantum level, effectively diluting its strength across the vast scales of the cosmos. Alternatively, the symmetry breaking might have hidden gravity by trapping it in a specific configuration of the higher dimensional space, separating it from the other forces which remained accessible in our three-dimensional realm. The strength of the gravitational constant, that seemingly arbitrary number that sets how strongly masses attract, wouldn't be a fundamental input of the universe, but rather an output, a consequence, a leftover fossil, from the specific way this monumental symmetry-breaking event occurred eons ago. The force that shapes galaxies, then, would be a kind of cosmic echo of a lost perfection, a broken symmetry that made our structured, life-friendly universe possible. For centuries, the biggest question of all has lingered over science and philosophy alike. How did everything begin? The prevailing answer for decades has been the Big Bang, a singular moment of infinite density and temperature where the laws of physics as we know them simply break down. It is the ultimate edge of our understanding, a point where time itself seems to flicker into existence from a state of what? Nothingness. This singularity is not just a physical barrier. It is a conceptual void, a place where our equations explode into meaningless infinities and our story of the cosmos grinds to an unsatisfying halt. It suggests a definitive beginning, a moment of creation that physics, in its classical form, is utterly unequipped to describe. But what if this singularity is not a wall, but a doorway? What if the universe did not emerge from a point of infinite mystery, but from a previous state of existence, following the unbreakable laws of quantum physics? This is the profound promise of the 18th secret, an idea that uses the tools of quantum gravity to transform the Big Bang from a beginning into a transition. The key lies in recognizing that the singularity is a prediction of Einstein's classical theory of general relativity, a theory we already know is incomplete because it ignores the quantum world. When we bravely extend our thinking into the quantum gravitational realm, the terrifying singularity doesn't just get smoothed over, it can vanish entirely, replaced by a far more elegant and physically sensible origin story. One of the most compelling alternatives is the concept of the cosmic bounce. Imagine the history of the universe not as a line starting at a point, but as a circle, or more accurately, a continuous, eternal cycle. In this breathtaking vision, our expanding universe is not the first chapter, but merely the latest. It was preceded by a vast, ancient cosmos that eventually stopped expanding and began to contract under its own immense gravity. As it collapsed, it didn't crush itself into an infinitely dense point. Instead, thanks to the repulsive forces predicted by quantum gravity theories, be it from loop quantum gravity's granular space-time or from the effects of a quantum field, the collapse reversed. The universe reached a minimum finite size and then bounced, exploding outward in the event we now call the Big Bang. In this view, the Big Bang was not a beginning from nothing, but a rebirth from a previous cosmic phase. Time did not have a start. It has always been flowing through an endless cycle of expansion, contraction, and renewal. The singularity is erased, replaced by a grand, cosmic heartbeat. An even more radical proposal comes from the brilliant mind of Stephen Hawking and his collaborator James Hartle. Their no-boundary proposal suggests that the question, what was before the Big Bang, is itself a misconception, a bit like asking what is north of the North Pole. Hawking and Hartle applied the strange rules of quantum mechanics to the entire universe. In the quantum world, particles don't follow single, defined paths. They explore all possible paths simultaneously. Hawking suggested that the early universe did the same thing. If we could run the clock backwards towards the Big Bang, time would begin to lose its classical, clock-like character. It would become fuzzy and probabilistic, eventually behaving more like a dimension of space. In this incredible quantum fog, there is no sharp, singular starting point, no boundary. The universe would be a completely self-contained, finite entity without an edge in time, much like the surface of a sphere has no edge. The Big Bang becomes not a point in time, but a location in the history of the universe where the nature of reality itself transforms from a quantum blend of space and time into the classical, flowing time we experience today. It's an origin without a beginning, a smooth, continuous emergence of time from a state where time, as we understand it, did not yet exist. These ideas are not just philosophical speculation. They are grounded in the actual mathematics of quantum fields and quantum geometry. The violent quantum fluctuations that define the vacuum are not just a side effect. They are the protagonists in this story. In the unimaginably dense environment of the pre-bounce universe, or at the fuzzy no-boundary beginning, these fluctuations wouldn't be small ripples on a calm sea. They would be the sea. The geometry of spacetime itself would be a roiling, probabilistic foam, And this inherent quantum jitter would provide the necessary energy to prevent the infinite collapse of a singularity. It's the ultimate example of the quantum world, saving the classical world from its own paradoxes. The force that might have powered the bounce or facilitated the no-boundary condition is the same vacuum energy we've encountered before. But here it acts not as dark energy, but as a cosmic repulsor, a quantum pressure that ensures the story of the universe has no true end, and therefore, no true beginning in the classical sense. This shifts our perspective from a universe that was created to a universe that simply is, eternally evolving according to the deepest laws of quantum physics, with our own Big Bang merely one magnificent event in its infinite history. Imagine the fabric of spacetime not as a perfectly elastic rubber sheet that always snaps back to its original form, but more like a slab of clay or a block of memory foam. When a powerful force presses into it, it might spring back almost completely, but it retains a tiny, permanent indentation, a subtle record of the disturbance that passed through. This is the essence of gravitational memory, a fascinating prediction of Einstein's theory where a passing gravitational wave doesn't just temporarily stretch and squeeze space. It leaves behind a permanent, albeit infinitesimal, deformation in the very geometry of the universe. Two objects floating freely in space, after a gravitational wave has passed, will not return to their exact original separation. They will be forever shifted by a tiny fraction of an atomic diameter, their new positions a silent testament to the wave that traveled through them billions of years ago. This effect is a direct consequence of the non-linear nature of general relativity. It's akin to the difference between a sound wave traveling through air and a tsunami wave traveling through the ocean. The sound wave passes and the air molecules return to their original positions, but the tsunami wave, with its immense power, can permanently reshape the coastline, moving vast quantities of sand and rock. In a similar, vastly more subtle way, a sufficiently strong gravitational wave, like those from the collision of two black holes, carries enough energy to etch a permanent change into the cosmic coastline of spacetime itself. For decades, this was seen as a curious theoretical footnote, an almost impossibly delicate effect that would forever be beyond our ability to measure. This is where the quantum world enters the story with a truly revolutionary proposition. That permanent deformation in spacetime isn't just a geometric scratch on the universe. According to some of the most cutting-edge ideas in theoretical physics, this deformation, this gravitational memory, might be physically encoded in the state of the quantum fields that permeate that region of space. Think of a quantum field as an incredibly sensitive film. A gravitational wave passes through it, and the field doesn't just jiggle and return to normal. Its very fundamental state is altered. The field's vacuum expectation value, its average energy configuration might be shifted, or more profoundly, the pattern of entanglement between different parts of the field could be permanently rewired by the passing wave. The gravitational memory would not just be a dent in space. It would be a specific, stable configuration of the underlying quantum fields, a frozen piece of data written into the fabric of reality. This transforms gravitational memory from a passive imprint into an active, readable record. It becomes a potential storage device for information about the most violent events in the cosmos. The specific pattern of the memory, the exact size and direction of the permanent shift, would encode details about the source that created the gravitational wave, like the masses and spins of the merging black holes. But if this memory is indeed stored in quantum fields, it could reveal so much more. By carefully probing this altered quantum state, physicists might be able to detect the subtle fingerprints of quantum gravity. Did the gravitational wave interact with virtual particles on its journey? Does the memory effect itself show signs of the discrete, granular structure of spacetime predicted by theories like loop quantum gravity? The quantum fields, by holding onto this memory, could act as a natural laboratory, preserving a wealth of information about the quantum aspects of gravity that are otherwise completely invisible to us. The monumental challenge, of course, is detection. How do you measure a permanent shift smaller than the width of a proton across distances of millions of light years? This is the realm of instruments of almost unimaginable precision, and the key lies not in looking for one single wave, but in building a statistical case over time. Gravitational wave observatories like LIGO, Virgo, and the future space-based LISA mission are essentially giant rulers designed to measure the tiny stretching of space. Their current method is to watch for the oscillatory signal of a wave as it passes the familiar chirp of a black hole merger. To detect memory, they would have to do something far more subtle. Compare the state of the detector before a wave arrives to its state long after the wave has passed, looking for that permanent offset shift. It's like trying to determine if an entire continent has moved a millimeter by comparing two photographs taken years apart. The strategy involves monitoring not just one event, but many. Each major gravitational wave event that passes through our local region of space would leave its own unique memory imprint on the quantum fields here. Over decades, as our detectors observe hundreds or even thousands of these cosmic collisions, these tiny, permanent shifts would accumulate. Advanced data analysis techniques would then sift through years of continuous detector data, searching for this cumulative drift against the ever-present background noise of quantum fluctuations and seismic rumbles. Finding it would be a triumph of experimental physics, but it would be so much more than that. It would be the first direct evidence that the universe itself has a long-term memory and that we can read its entries. It would open an entirely new window into the quantum nature of gravity, allowing us to use the universe's own recording mechanism to finally understand the force that shaped it. Now, let's explore a secret that reveals a stunning and deeply counterintuitive connection between motion, heat, and the very fabric of space-time. A phenomenon that suggests gravity itself might be a kind of cosmic mirage born from acceleration. Imagine you are an astronaut, floating in the deepest, darkest, most perfect vacuum of outer space. According to everything we know, you are completely alone, surrounded by nothingness. The temperature is absolute zero, and there is not a single particle to be found. But now, imagine you fire your rockets and begin to accelerate, cruising through the void at a constant, ever-increasing velocity. Something utterly bizarre happens. Your instruments' incredibly sensitive detectors suddenly start to ping. They report that you are no longer in a cold, empty void. You are now surrounded by a warm bath of particles, a gentle heat that wasn't there a moment before. You have not flown into a cloud of gas. The universe around you hasn't changed. The only thing that has changed is your own state of motion. This is the Unruh effect, a breathtaking prediction of quantum field theory that tells us an accelerating observer will perceive the quantum vacuum not as empty, but as a thermal bath of radiation, its temperature directly proportional to their acceleration. This isn't just a theoretical curiosity. It's a direct sibling to Hawking's famous discovery that black holes radiate heat. Hawking radiation arises because the intense gravitational field at a black hole's event horizon is, in a profound mathematical sense, equivalent to an acceleration. The Unruh effect completes this picture by showing that the reverse is also true. Acceleration creates a perceptual field that mimics a gravitational field. The temperature an accelerating observer measures is given by a beautifully simple formula. The acceleration multiplied by a fundamental constant, divided by the speed of light and other natural numbers. Crank up your acceleration, and the empty space around you appears to get hotter. To an observer hurtling through space with enough thrust, the vacuum would seem to glow with heat. This forces us to abandon the naive idea that the vacuum has a single objective state. What you see in the quantum world depends critically on your own journey through it. Reality itself is observer-dependent. This is where the connection to gravity becomes nothing short of revolutionary. Einstein's great insight, his equivalence principle, told us that there is no difference between being in a gravitational field and being in an accelerating rocket. If you were in a windowless spaceship, you couldn't tell if you were sitting on a launch pad on Earth or accelerating through deep space at 9.8 meters per second squared. The Unruh effect now adds a stunning quantum layer to this principle. It suggests that the connection is not just about how objects move, but about the very nature of reality they perceive. If an accelerating observer sees a thermal bath of particles, and acceleration is equivalent to gravity, then an observer sitting still in a gravitational field should also perceive a thermal bath. The force of gravity might inherently have a temperature associated with it. This leads to the breathtaking idea that a gravitational field is fundamentally thermal in nature. An object held fixed in a gravitational field, resisting the pull to fall, is in a state of perpetual acceleration. It's constantly pushing against the pull of gravity to stay in place. According to the logic of the Unruh effect, this should mean that the space around it is filled with a glow of radiation, a heat that is a direct consequence of the gravitational field itself. This thermal energy isn't coming from anywhere. It emerges from the interaction between the quantum fields and the accelerated frame of reference. This is the secret that truly blurs the line between thermodynamics and gravity, suggesting that the force that organizes the cosmos is intimately, perhaps fundamentally, linked to heat and entropy. The equations that describe this thermal gravity are formally identical to the laws of thermodynamics, hinting that gravity might not be a force in the traditional sense, but a statistical, emergent property of a system, the universe tending toward a state of higher disorder. In this view, the pull you feel toward the Earth is not a direct attraction, but the thermodynamic gradient of the universe, a tendency for the quantum information of the vacuum to maximize its entropy, with gravity as its most visible and powerful expression. But to truly grasp the bizarre consequences of this marriage, we must journey to the most extreme environment we know, the edge of a black hole. Imagine a pair of virtual particles, a particle and its antiparticle, spontaneously flashing into existence from the quantum vacuum just outside the event horizon. This is a common occurrence, a loan of energy from the universe that is almost instantly repaid when the two particles collide and annihilate. However, in the intensely warped spacetime right at the precipice of a black hole, a cosmic robbery can occur. The gravitational tidal forces are so immense that they can violently rip these two particles apart before they have a chance to recombine. One particle falls across the event horizon, forever lost to the black hole, while the other, its partner now severed, escapes into space as a genuine, permanent particle. From the perspective of an observer far away, this process looks like a steady stream of radiation emanating from the black hole itself. This is Hawking radiation, the stunning prediction that black holes are not eternal prisons but slowly evaporate, losing mass as they radiate. The energy for this created particle comes from the mass of the black hole. The infalling particle that was captured has negative energy, effectively reducing the black hole's total mass. This is the ultimate demonstration of how gravity, through the curvature of spacetime, doesn't just influence quantum fields, it forces them to create something from what was once nothing, directly linking the fate of the largest objects in the universe to the smallest fluctuations of the quantum world. This particle creation isn't unique to black holes. It's a universal phenomenon in any dynamically curved spacetime. The expansion of our own universe acts as a far gentler, but equally profound, engine for this effect. In the very early moments of the cosmos, during the period of rapid inflation, space-time expanded at an exponential rate. The quantum fields that filled this newborn universe were being stretched along with it. This rapid stretching acted to amplify the natural fluctuations of these fields, pulling virtual particles apart and promoting them into real, long-lived entities. The tiny, microscopic quantum jitters in the gravitational field itself were stretched to astronomical sizes, freezing into the fabric of the expanding universe. These frozen ripples in spacetime became the seeds for all the large-scale structure we see today, the vast cosmic web of galaxies and galaxy clusters. The gentle temperature variations we observe in the cosmic microwave background, the afterglow of the Big Bang, are the direct imprint of these primordial quantum fluctuations, magnified by the gravitational expansion of the universe. This means every galaxy, every star, every planet, and by extension, every one of us, owes our existence to this magnificent collaboration between quantum fields and curved spacetime. The microscopic and the macroscopic are inextricably linked, with gravity serving as the great amplifier that turned quantum noise into the architecture of the cosmos. This two-way street between quantum fields and gravity reveals a breathtaking feedback loop that hints at a far deeper unity. We've seen how gravity curves space-time and forces quantum fields to create particles. But those created particles themselves carry energy, and according to Einstein, all energy curves spacetime. So the particles created by the curved spacetime go on to further curve the spacetime themselves. It's a self-referential loop where the actors reshape the very stage upon which they perform. This back reaction is a crucial piece of the puzzle in understanding the complete life cycle of a black hole. As a black hole emits Hawking radiation and loses mass, its gravitational field weakens, its event horizon shrinks, and the rate of particle production changes. The quantum fields are not passive passengers, they are active participants in the evolution of gravity itself. This complex dance suggests that a full theory of quantum gravity won't just be a theory of quantized spacetime, but a theory where spacetime and the quantum fields that live within it are co-dependent partners, emerging together from a more fundamental, unified description of reality. The phenomena of Hawking radiation and inflationary seeding aren't just interesting curiosities. They are the observable signatures of this profound partnership, the clues that are guiding us toward the final unification of physics. Now we arrive at one of the most profound and deeply philosophical puzzles at the heart of unifying gravity with the quantum world. A problem so fundamental it challenges our very understanding of cause and effect, of before and after. This is the notorious problem of time. In the pristine, mathematical world of quantum mechanics, time plays the role of a steadfast, universal conductor. It is an absolute, external parameter against which the wave functions of particles evolve. The famous Schrödinger equation treats time as a background stage, an independent variable that ticks away with impartial regularity, everywhere and for everyone. It is the ultimate clock, outside the system, dictating the rhythm of quantum change without ever being influenced by it. But when we step into the curved universe of general relativity, this dependable conductor vanishes. Einstein's theory tells us that time is not absolute. It is relative, malleable, and deeply personal. Your clock runs at a different rate depending on your speed and the strength of the gravitational field you are in. Time is not a background stage. It is one actor in a four-dimensional ballet called space-time, and it is dynamically intertwined with space and matter. The equations of general relativity are fundamentally timeless. They describe the universe as a static, four-dimensional block where the past, present, and future all equally exist. The feeling of time flowing is, in this view, perhaps just a human illusion. This creates a catastrophic conflict when we try to merge the two theories. Quantum mechanics needs its external time to evolve, but in a theory of quantum gravity, there is no outside. The universe is the entire system. If time is relative and dynamic, what serves as the clock for the wave function of the entire cosmos? This is where quantum fields might offer a path forward, not by providing a single answer, but by radically redefining the question. One compelling proposal suggests that time does not exist as a fundamental ingredient at all. Instead, it might be an emergent property, a useful illusion that arises from the changing relationships between quantum fields. Think of the universe not as existing in time, but as a vast, frozen network of correlations. All that fundamentally exists are the quantum fields and their relationships to one another. What we perceive as the passage of time could be nothing more than our perception of these correlations changing. For example, the movement of a clock's hand is just a correlation between the configuration of the clock's particles and the configuration of particles in your brain. Time emerges from this web of interconnectedness. In this view, the universe is static, and time is simply the way we order memories of different configurations of these quantum fields. It's a powerful idea that dissolves the problem by stating that time isn't a thing to be quantized. It's a story we tell about change. Another approach, deeply rooted in the practical challenges of building a quantum gravity theory, is to find a suitable internal clock within the universe itself, a physical process that can serve as the time variable for everything else. Since there is no external clock, the universe must tell its own time. This is where the dynamics of quantum fields become essential. Certain fields, as they evolve, could provide a natural, preferred time variable against which other changes can be measured. For instance, in the very early universe, the inflatoned field, the field responsible for the rapid expansion of inflation, could have rolled down its energy hill at a steady, predictable rate. This rolling could have served as the master clock for the entire cosmos during that epoch, providing a well-defined notion of time that everyone could agree on, even in the absence of a background. In our current universe, the overall expansion of the cosmos, measured by the Hubble parameter, might provide a crude cosmic time, or perhaps the relentless increase of entropy, the arrow of time dictated by thermodynamics, is the true driver. These proposals all point to a universe where time is not handed down from on high, but is distilled from the complex, evolving interactions of the quantum fields that make up everything. The problem of time forces us to accept that our most intuitive experience of reality might be a derivative phenomenon, a compelling narrative woven by the endless dance of fields from which both space and time are born. This perspective invites us to consider the very fabric of reality as a vast, dynamic information processor. If gravity is indeed an entropic force, then the force we feel pulling us toward the Earth is not a fundamental attraction between masses, but a statistical tendency for the universe to maximize the disorder of the information encoded on these invisible screens. The reason an apple falls is not because the planet is pulling on it, but because that is the direction in which the entropy of the cosmic information increases. This turns our understanding of cause and effect completely on its head. Gravity isn't the cause of the motion, it is the manifestation of the effect. It is the universe's way of organizing itself into the most probable configuration, and the gradient of that probability is what we have always called a force. Quantum fields enter this picture as the ultimate media for this cosmic information storage. Think of these fields not as ethereal substances, but as the fundamental hard drives of reality. Every particle, every fluctuation, is a bit of data. The holographic principle suggests that all the information describing a three-dimensional volume of space is actually encoded on a two-dimensional surface bounding that region. The quantum fields are what hold that information. They are the pixels on the cosmic screen, and their ever-changing states represent the flow of information. When matter or energy enters a region of space, it changes the information content on the boundary screen. The system then responds to this change by redistributing itself to maximize entropy, and this response manifests as a gravitational force. In this breathtaking view, the quantum fields are not just influenced by gravity. They are the substrate from which gravity emerges. The gravitational field is the gradient of the information stored in these fields, a direct readout of how the information density changes from one point to another. This idea finds a powerful analogy in the world of thermodynamics and elasticity. Imagine a stretched elastic membrane like the surface of a balloon. If you place a weight on it, the membrane deforms. The deformation is not a fundamental property of the rubber. It emerges from the collective interactions of its molecules responding to the stress. In the same way, gravity could be an emergent property, an elastic response of spacetime itself, driven by the need to maximize information entropy. The equations that describe this entropic force bear a striking and beautiful resemblance to Einstein's field equations of general relativity, suggesting that his magnificent description of gravity as geometry might itself be an emergent consequence of a deeper, information-theoretic reality. This doesn't diminish Einstein's work. It provides a potential explanation for why spacetime behaves the way it does, revealing the hidden, informational mechanics behind the geometric curtain. The quantum fields are the vibrating strings of this cosmic instrument, and gravity is the harmonious sound that emerges from their collective song. Now let's explore a phenomenon so strange it seems to defy common sense, yet it provides one of the most compelling laboratory hints that gravity might indeed emerge from the quantum void. Imagine two perfectly smooth, neutral metal plates placed incredibly close together in a perfect vacuum, separated by a gap narrower than 1,000th the width of a human hair. According to classical physics, nothing should happen between them. There's no gravity to speak of at this scale, no electric charge to pull them together. They should remain motionless, indifferent to each other's presence. But in reality, something extraordinary occurs. The plates experience a faint but undeniable pull toward each other, snapping together if not held firmly in place. This is the Casimir effect, a bizarre and beautiful demonstration of the quantum vacuum's hidden power, and it may hold a profound secret about the nature of gravity itself. The force that draws these plates together doesn't come from anything tangible between them, but from the absence of something, and specifically, the absence of certain quantum fluctuations. Remember that the vacuum is not empty. It's a seething sea of virtual particles constantly popping in and out of existence. These fluctuations aren't random, they occur at every possible wavelength, like an infinite orchestra playing every note simultaneously. Now, when you place two plates extremely close together, you impose a boundary condition on this quantum orchestra. Just like the air in an organ pipe can only vibrate at certain resonant frequencies, the quantum fields between the plates can only support fluctuations whose wavelengths fit perfectly into the gap. Long wavelength vibrations, those larger than the gap between the plates, are simply too big to fit, and are therefore excluded from the space between them. This creates a dramatic imbalance. Outside the plates, the quantum vacuum is buzzing with fluctuations of all wavelengths, long and short. But in the narrow gap between them, only the shorter wavelengths can exist. The radiation pressure from this lopsided sea of virtual particles, greater on the outside of the plates than on the inside, pushes the plates together. It's as if you were in a crowded room and everyone was pushing against the walls. If you suddenly removed all the people from the center, the walls would be pushed inward by the pressure from the outside. The Casimir force is this inward push, a direct, measurable consequence of the quantum vacuum's energy and the boundaries we place upon it. The stunning implication of this effect is that it provides a tangible, microscopic model for how empty space can generate an attractive force. And this is where the connection to gravity becomes irresistible. The force of gravity, as we experience it on a cosmic scale, is also an attractive force between masses. What if, just like the Casimir force, it too is a result of a pressure imbalance in the quantum vacuum, Imagine the entire universe not as a stage with objects on it, but as a cosmic Casimir setup. A massive object like a planet or a star doesn't just sit in space. It imposes a boundary condition on the quantum fields around it. Its presence could exclude certain long-wavelength vacuum fluctuations from its immediate vicinity, creating a region of lower quantum pressure near its surface. Other objects would then be pushed toward it by the relatively higher pressure of the vacuum further out. In this breathtaking analogy, the gravitational attraction we feel could be the cosmological scale version of the Casimir effect, not a fundamental pull, but an emergent push caused by the way mass sculpts and structures the energetic vacuum around it. This idea transforms our view of the vacuum from a passive backdrop into an active participant in shaping the forces of nature. The quantum fields are not just buzzing with energy. Their energy density can be altered by the presence of boundaries and masses. The Casimir effect shows us this directly in the lab. Gravity could be the same phenomenon, playing out across the vast expanse of the universe. It suggests that the force that holds galaxies together and the force that pulls two tiny metal plates together are not different in kind, but only in scale. Both are manifestations of the vacuum's tendency to minimize its energy, to find the most probable configuration for its fluctuations. This provides a powerful unifying thread, linking the bizarre, counterintuitive world of quantum mechanics with the grand, gravitational architecture of the cosmos, all through the silent, invisible, but immensely powerful activity of the quantum fields that fill the void. But in the grand cosmic ledger, where does gravity fit? This brings us face to face with what many physicists consider one of the most glaring and puzzling imbalances in all of nature: the hierarchy problem. This isn't just a small discrepancy, it's a chasm of unimaginable proportions. The force of gravity is 10 to the 36 times weaker than the electromagnetic force. To put that number into perspective, that's a 1 followed by 36 zeros. It is the difference between the strength of a single person's arm and the combined gravitational pull of our entire galaxy. A tiny refrigerator magnet can effortlessly overcome the gravitational pull of the entire Earth, a planet weighing over 6 sextillion tons. This isn't a minor curiosity. It's a screaming anomaly that suggests something fundamental is missing from our picture of the universe. Why would nature create a force so pathetically feeble compared to its siblings? Is this weakness a random, accidental feature of our cosmos? Or is it a profound clue pointing toward a deeper layer of reality? The hierarchy problem becomes especially sharp when we look at the Higgs boson, the particle that gives all others their mass. In the quantum world, the mass of the Higgs is extremely sensitive to corrections from its interactions with other particles. Virtual particles flashing in and out of existence should contribute enormous energy to the Higgs field, driving its expected mass up to a scale 1 trillion times larger than it actually is, a scale known as the Planck mass, where gravity becomes strong. This is like carefully balancing a pencil on its tip, only to have a constant hurricane blowing around it. Stability seems impossible. The fact that the Higgs mass, and by extension the entire electroweak scale, remains so relatively small and stable in the face of these quantum corrections seems to require an absurdly precise and seemingly unnatural fine-tuning of the underlying physics. It's as if the universe is performing a miraculous high-wire act, and we are left wondering what invisible mechanism is keeping it from falling. This is where our quantum fields and the secrets they hold offer not just an answer, but a complete reframing of the question. The incredible feebleness of gravity might not be a problem to be solved, but the most important clue we have, a cosmic signpost pointing directly toward new physics. Two of the most compelling ideas that emerge from quantum field theory, supersymmetry and extra dimensions, turn the hierarchy problem on its head. They don't try to explain why gravity is weak. They instead provide elegant mechanisms that naturally predict its weakness as a consequence of a more symmetric and expansive reality. First, let's consider supersymmetry. This beautiful theory proposes that for every known particle in the Standard Model, there exists a hidden super-partner particle. For every quark, a squark; for every electron, a selectron. This isn't just a doubling for fun. It introduces a powerful new symmetry between the two fundamental classes of particles, force-carrying bosons and matter-making fermions. This symmetry has a breathtaking consequence for the hierarchy problem. For every Standard Model particle that contributes a large, positive quantum correction to the Higgs mass, its superpartner is predicted to contribute an identical but negative correction. They are perfect canceling partners in a cosmic dance, gracefully and naturally keeping the Higgs mass stable and small without any need for miraculous fine-tuning. In this view, gravity isn't anomalously weak. The other forces are being artificially protected and kept strong by this underlying supersymmetric balance. The hierarchy problem is solved by the elegant mathematics of partnership. The second revolutionary idea comes from the possibility of extra-spatial dimensions, as proposed by theories like string theory. Imagine our universe as a three-dimensional membrane, or brane, floating within a higher dimensional space. In this scenario, the particles of the Standard Model electrons, quarks, photons, are like waves trapped on the surface of this membrane. They cannot leave its surface, but the gravitational field and its hypothesized carrier, the graviton, is different. It is not confined to our brane. It can propagate into the full volume of the higher dimensional bulk. This simple difference changes everything. If gravity's influence can spread out into these extra dimensions, its strength would become diluted from our three-dimensional perspective. Imagine a light bulb in the center of a large room. If you were right next to it, it would seem very bright. But if that same light bulb were the only source of illumination for an entire sports stadium, its light would be diffused and appear much dimmer from any single seat. In exactly the same way, gravity might appear weak to us not because it is fundamentally feeble, but because we are only experiencing a tiny fraction of its true strength. The rest is leaking away into dimensions we cannot perceive. The hierarchy problem vanishes, replaced by a geometric explanation for gravity's ghost-like presence. Both of these ideas, born from the mathematics of quantum fields, transform our perspective entirely. The staggering difference in strength between gravity and the other forces is no longer an embarrassing puzzle. It becomes the most valuable piece of evidence we have, a direct signal from the hidden architecture of the universe. It is the whisper of superpartners waiting to be discovered at unimaginably high energies, or the faint echo of unseen dimensions curled up at every point in space. The hierarchy problem is the thread that, when pulled, could unravel the entire tapestry to reveal a reality far grander, more symmetric, and more beautifully structured than we ever dreamed. The weakness of gravity is not a bug in the code of the cosmos. It is the feature that allows us to read it. But if the quantum vacuum can create particles, then perhaps the most profound demonstration of its power is found in the most extreme gravitational environment imaginable, the black hole. It was here that Stephen Hawking made a discovery that would forever link the fate of these cosmic monsters to the humble laws of thermodynamics, revealing a secret so deep it suggests that gravity, at its core, is not a force of mechanics, but a force of heat and information. In the 1970s, Hawking applied the strange rules of quantum field theory to the warped spacetime just outside a black hole's event horizon. He found that the intense gravitational field would violently tear apart the virtual particle pairs constantly flashing in and out of the vacuum. In this cosmic robbery, one particle falls into the black hole, while its partner escapes into space. To a distant observer, this process looks like a steady stream of radiation emanating from the black hole itself. This Hawking radiation has a temperature, and it carries away energy, meaning black holes are not eternal. They slowly evaporate, losing mass over astronomical timescales until they potentially vanish entirely. This was a monumental revelation. A black hole, the simplest object in the universe defined only by its mass, spin, and charge, somehow has a temperature. And where there is temperature, there must be entropy. Entropy is a measure of disorder, of the number of ways a system's microscopic parts can be arranged while still looking the same from the outside. A hot cup of coffee has higher entropy than a cold one because its molecules are in a more chaotic, disordered state. Jacob Bekenstein, a colleague of Hawking's, first proposed that black holes must have entropy, and an enormous amount of it. Hawking's calculation confirmed this and provided the precise formula. The entropy of a black hole is exactly 1/4 of the area of its event horizon, measured in Planck units. This is a staggering result. In every other system we know, entropy is proportional to volume. A larger box can contain more disordered arrangements of particles than a small one. But for a black hole, entropy is proportional to its surface area. This single fact is the strongest hint we have that our intuitive, three-dimensional view of reality might be an illusion, and that the true description of the universe might be encoded on a two-dimensional surface. The holographic principle in its purest form. This intimate link between a black hole's area and its entropy forged an unbreakable bond between gravity and thermodynamics. The laws of black hole mechanics, derived from Einstein's equations, were found to be mathematically identical to the laws of thermodynamics. The event horizon's area, which always increases when matter falls in, is analogous to entropy. The surface gravity at the horizon is analogous to temperature. This is no mere analogy. It appears to be a fundamental identity. Gravity is thermodynamics. The force that curves space-time is a manifestation of the universe's relentless drive toward disorder. But this raises a monumental question. If a black hole has entropy, what are the microscopic, quantum mechanical states that this entropy is counting? What are the countless individual parts whose different arrangements give rise to this immense disorder? For a gas, it's the positions and momenta of all its molecules. For a black hole, the answer must lie in the quantum fields that live on, or just outside, its event horizon. This is where the quantum fields themselves become the heroes of the story. The event horizon is not a passive, one-way membrane. It is a region of incredibly intense energy and activity. The quantum fields there are in a highly excited state, furiously fluctuating due to the extreme gravitational tidal forces. It is now widely believed that these quantum fluctuations on the horizon are the fundamental degrees of freedom, the individual moving parts, that account for the black hole's entropy. Every possible configuration of these field fluctuations, every twist and vibration, represents a specific microstate of the black hole. The vast area of the horizon provides the canvas, and the quantum fields provide the paint, creating a masterpiece of information storage. The entropy is a measure of the logarithm of the number of ways these fields can be arranged on that surface. This means that the information about everything that ever fell into the black hole isn't lost inside its mysterious interior. It is smeared out and stored in the intricate patterns of these horizon-bound quantum fields, a frozen hologram of the black hole's history. The implications of this for a theory of quantum gravity are nothing short of revolutionary. It tells us that any successful theory must be inherently thermodynamic. It cannot be a classical theory of smooth geometry alone. It must be a statistical theory, much like the theory of gases. Einstein's beautiful equations of general relativity, which describe the deterministic curvature of spacetime, would then be the equivalent of the equations of thermodynamics for a gas. They describe the large-scale, average behavior that emerges from the chaos of countless microscopic parts. The true, fundamental theory would be the statistical mechanics of those parts, which we now believe are the quantum states of the fields on the horizon. This flips the entire problem on its head. We are not trying to quantize gravity. We are trying to find the microscopic theory whose thermodynamic limit is gravity. The force that holds the universe together is not a fundamental interaction but an emergent phenomenon, a thermodynamic tendency toward maximum entropy. And the curvature of spacetime is the way the universe organizes itself to achieve it. This secret, written in the heat of black holes and the entropy of their horizons, may be the final clue that gravity was never a force to begin with, but the cosmic expression of information itself. Now we arrive at a secret that takes us to the very edge of conceptual understanding, to an equation so radical it attempts to describe the entire universe in one breath, but in doing so, seems to erase one of our most fundamental experiences from the ledger of reality. This is the Wheeler-DeWitt equation, a bold and controversial masterpiece that emerges when we try to weld quantum mechanics directly onto the framework of general relativity. Its most shocking feature is not what it contains, but what it glaringly omits, the variable for time. In this breathtaking formulation, the universe is described as a static, frozen block, a single, stationary wave function for all that exists, where the concepts of before and after have no mathematical meaning. It portrays a cosmos without change, without history, without evolution. It is a timeless picture of a universe that simply is, and this profound strangeness may hold the key to understanding how time itself emerges from a more fundamental, timeless reality. The equation itself is the result of applying the standard rules of quantum mechanics to the entire cosmos. In quantum theory, a particle is described by a wave function that evolves in time according to the Schrödinger equation. The Wheeler-DeWitt equation is essentially the Schrödinger equation for the universe itself. But when you plug in the ingredients of general relativity, where time is relative and dynamic, the time variable cancels out completely. It vanishes. The resulting equation h psi equals 0 is known as the Hamiltonian constraint. It states that the total energy of the universe, when you account for both matter and the energy of the gravitational field itself, is exactly 0. But more importantly, it describes a universe that is static. The wave function psi doesn't evolve, it just is. This presents a monumental paradox. We experience a world of relentless change, of flowing time, yet our most ambitious attempt to create a quantum theory of gravity describes a reality that is utterly frozen. This is the heart of the problem of time in quantum gravity, and it suggests that our perception of time may not be a fundamental feature of the universe, but a powerful illusion that emerges from something deeper. This is where the dynamics of quantum fields offer a potential escape from this frozen wasteland, a way to breathe the illusion of change back into a timeless cosmos. The proposal is that time does not exist as a fundamental background parameter, but emerges from the changing relationships between quantum fields. Imagine the entire universe as a single, vast network of correlations. All that truly exists are the quantum fields in a specific, stationary state described by the Wheeler-DeWitt equation. What we perceive as the passage of time could be nothing more than our journey through this network of correlations. For instance, the movement of a clock's hand is not happening in time. It is a correlation between the configuration of the clock's particles and the configuration of the particles in your brain that constitute your memory. Time emerges from this complex web of interconnectedness. It is a story we tell ourselves about change, but the underlying reality is a single, timeless snapshot. In this view, the quantum fields themselves become the ultimate clocks. Their evolving configurations provide an internal, relational measure of change that we then interpret as time. Think of a simple universe containing only two fields, the electromagnetic field and a scalar field like the Higgs field. The value of the Higgs field could be used as a clock. As its value changes, it correlates with changes in the electromagnetic field, perhaps causing particles to gain mass or forces to interact differently. An observer within this universe would perceive these correlated changes as events unfolding in time, with the Higgs field value serving as the hands of the clock. Yet, from the outside perspective of the Wheeler-DeWitt equation, all these configurations, all the different values of the Higgs field and their correlated states, exist simultaneously in a vast, timeless superposition. Time is not a river flowing. It is a landscape we are walking through, and our conscious experience of a moment is simply our position on that landscape. The quantum fields provide the topography, and their interrelationships create the compelling, unidirectional illusion of a past, present, and future, weaving the fabric of time from the timeless threads of quantum connection. Perhaps the most controversial and speculative intersection in all of modern physics lies at the crossroads of quantum gravity and the human mind. This is a realm where solid science meets profound philosophy, a space where the deepest mysteries of the cosmos collide with the deepest mystery of all, the nature of our own conscious experience. The core idea, championed by a small number of physicists and philosophers, suggests that the phenomena of quantum mechanics and gravity might not just be involved in brain function, but could be fundamentally necessary to explain how a physical brain gives rise to subjective awareness. It's a tantalizing, if highly speculative, notion that the force that holds the universe together might also play a role in weaving the fabric of consciousness itself. One of the most prominent figures in this arena is the renowned physicist Sir Roger Penrose. Alongside anesthesiologist Stuart Hameroff, Penrose proposed the Orchestrated Objective Reduction Model, or ORCH. Their theory begins with a central problem in neuroscience. The seemingly warm, wet, and chaotic environment of the brain appears, at first glance, to be utterly hostile to the delicate state of quantum coherence, where particles maintain a ghostly connection. Quantum states are notoriously fragile, typically collapsing when they interact with their environment, a process known as decoherence. How could such delicate processes survive in the busy, biochemical soup of our neurons? Penrose and Hameroff suggest that the answer might lie deep within the cells, in structures called microtubules. These are tiny, cylindrical proteins that form the skeleton of neurons, and the theory proposes they are engineered to protect quantum information. Their proposal is that consciousness arises from quantum computations happening within these microtubules, but that's only half the story. The other half is gravity. Penrose argues that the collapse of the quantum wave function, the moment a probability becomes a definite reality, is not a random event, but an objective process triggered by gravity. In his view, when a quantum system becomes too massive or its superposed states become too separated in spacetime, its own gravitational self-energy causes it to spontaneously and objectively collapse into a single state. In the brain, the idea is that quantum superpositions within the microtubules grow until they reach a critical threshold of mass-energy separation, at which point gravity steps in and orchestrates their collapse. Each collapse event is a moment of definite reality, and a cascade of these events is what we experience as a stream of consciousness. In this model, gravity is not just a background force. It is the conductor of the quantum orchestra in our brains, the mechanism that transforms potentiality into actualized experience. While the ORCH or theory remains firmly on the fringe of mainstream physics, and is met with significant skepticism regarding the feasibility of quantum coherence in the brain, its true value may lie in its boldness. It demonstrates how the profound mystery of gravity inspires thinkers to bridge seemingly unrelated domains. The enigma of how quantum probability resolves into classical certainty mirrors the puzzle of how the objective firing of neurons gives rise to subjective feeling. By proposing gravity as the link between these two puzzles, Penrose challenges us to consider a universe that is far more deeply interconnected than we imagined, where the laws of the very large are intimately involved in the phenomena of the very complex. This speculative journey serves a crucial purpose beyond any single theory's validity. It highlights the vast, uncharted territory that remains once we move beyond the comfortable confines of established science. The hard problem of consciousness, why and how physical processes in the brain create a subjective, inner life, remains one of the greatest unsolved questions. The equally hard problem of quantum gravity, how to reconcile the smooth geometry of spacetime with the fuzzy probabilities of the quantum world, stands as the other. That these two ultimate frontiers might be connected is a powerful testament to human curiosity and our drive to find unified answers to nature's deepest puzzles. It shows that the mystery of gravity doesn't just captivate physicists. It inspires a much broader quest for understanding, pushing the boundaries of thought and reminding us that sometimes the most radical ideas are the ones that expand our imagination, even if they ultimately guide us toward more grounded truths. For all the breathtaking elegance of these theories, from strings and loops to emergent spacetime, they remain suspended in the realm of mathematical beauty until they can be tested against the hard, unforgiving data of experiment. This is the grand challenge of our 29th secret. How do we possibly probe a realm that operates at a scale a billion times smaller than an atom and requires energies a quadrillion times higher than our most powerful machines can produce? The answer lies not in a single, monumental experiment, but in a symphony of ingenious, indirect approaches that are already pushing the boundaries of what we can measure, each one designed to catch a faint whisper of quantum gravity in the cosmic noise. One of the most promising and delicate techniques is atom interferometry. Imagine taking a single atom and splitting its quantum wave function, sending one half on a path that is just a fraction of a millimeter higher than the other, and then recombining them. The difference in gravitational pull between those two paths creates an exquisitely sensitive phase shift in the atom's wave function, an interference pattern that can be measured with astounding precision. These devices are, in effect, the most sensitive rulers ever built, capable of detecting changes in the gravitational field so tiny they were once thought immeasurable. Researchers are now using these quantum rulers to search for deviations from Newton's inverse square law at microscopic distances. If spacetime is indeed granular at the Planck scale, as loop quantum gravity suggests, or if extra dimensions are curled up and altering how gravity behaves on tiny scales, as string theory predicts, these atom interferometers could detect the faint signature of that structure. They are not looking for gravitons directly, but for the telltale footprints they might leave in the fabric of spacetime itself, a subtle warping that would betray gravity's quantum origins. On the opposite end of the scale, astronomers are turning the cosmos itself into a laboratory through the precise timing of pulsars. These celestial lighthouses are the spinning cores of dead stars, emitting beams of radio waves with a regularity that rivals the most precise atomic clocks. As these pulses travel across the galaxy to reach our telescopes, they can be minutely distorted if they pass through a sea of gravitational waves, the ripples in spacetime produced by the motion of massive objects. By meticulously monitoring networks of these pulsars for decades, projects like NanoGrav are creating a galaxy-sized gravitational wave detector. The specific statistical pattern of the timing irregularities in these pulses could hold a revolutionary secret, a background hum of gravitational waves from the very early universe, potentially generated by quantum fluctuations during the period of inflation. Detecting this primordial background would be like listening to the echo of the Big Bang itself, and encoded within its frequency could be the faint signature of quantum gravity at work in the universe's first moments, a fossilized imprint of when spacetime itself was being forged. Meanwhile, the quest continues to create microscopic black holes or other quantum gravitational phenomena in the high-energy collisions of particle accelerators like the Large Hadron Collider. The idea is audacious. If extra spatial dimensions exist, they could lower the energy threshold at which gravity becomes strong. At the LHC, protons are smashed together at velocities approaching the speed of light, concentrating an immense amount of energy into a vanishingly small point. In a universe with large extra dimensions, this could be enough to briefly warp spacetime so severely that a microscopic black hole would blink into existence, evaporating instantly into a shower of particles via Hawking radiation. While no such events have been conclusively observed, the relentless search continues. Even the absence of a signal is valuable data, constraining the possible sizes and properties of these hidden dimensions and forcing theorists to refine their models. It is a process of elimination and discovery, using the most complex machine ever built to punch a hole into the quantum gravitational realm, if only for a fleeting instant. The future holds even more promise with next-generation observatories. The space-based gravitational wave detector, LISA, will open a new low-frequency window on the cosmos, allowing us to listen to the mergers of supermassive black holes. The precise shape of their gravitational wave signals could reveal the quantum structure of the black holes themselves, whether their event horizons have a fuzzy, quantum atmosphere, or if their ring-down phase shows deviations from Einstein's pure predictions, hinting at those crucial quantum corrections. Similarly, increasingly detailed maps of the cosmic microwave background from telescopes will scour the polarization patterns of this ancient light for the faint imprints of primordial gravitational waves, a direct probe of the universe when it was a quantum gravitational system. Each of these experiments is a different path up the same mountain, a multi-front assault on the final great problem in physics. They may not provide a single eureka moment, but rather a convergence of evidence, a mosaic of clues that together will finally reveal the quantum heart of gravity. The cosmological constant stands as perhaps the most infamous number in all of physics, a single term in Einstein's equations that represents the energy density of the vacuum itself, a seemingly uniform, invisible energy that fills empty space and drives the accelerating expansion of the universe. Its observed value is astonishingly small, yet the most straightforward calculation from quantum field theory predicts a number that is wrong by a factor of 1 followed by 120 zeros. This isn't just a minor miscalculation. It is the largest discrepancy between theory and observation in the entire history of science. If the quantum vacuum truly held the staggering energy that the math suggests, its gravitational effect would have curved the universe into a microscopic knot within the first instant of the Big Bang. The fact that we exist in a vast, aging cosmos means something is profoundly wrong with our understanding, and the resolution to this crisis may lie in a deeper understanding of the quantum fields themselves. The root of the problem is that we are likely asking the wrong question. The standard approach calculates the vacuum energy by summing up the zero-point energies of all the quantum field modes, down to the Planck scale. This is like trying to measure the mass of the ocean by adding up the mass of every single water molecule. While technically correct in a narrow sense, it misses the larger, emergent picture. The quantum fields are not passive reservoirs of a fixed energy. They are dynamic, interacting entities. The key to solving the cosmological constant problem may not be in finding a magical cancellation for this enormous calculated energy, but in realizing that this energy does not gravitate in the way we have traditionally assumed. In the emergent gravity paradigm, the vacuum energy is not a source that curves spacetime. It is the very substance from which spacetime itself is constructed. The incredible energy of the quantum fluctuations isn't a problem to be subtracted away. It is the essential ingredient that gives rise to the gravitational force in the first place, through the entropic or holographic principles we've discussed. Its value isn't small. Our perspective on its role is simply incorrect. Another compelling possibility is that the cosmological constant isn't a constant at all. Instead of being a fixed parameter of the universe, it could be a dynamic field, often called quintessence, that evolves over time. Imagine a quantum field that started with a high energy density in the early universe, but has been slowly rolling down a gentle potential hill, its energy dissipating over billions of years. By the present day, it has naturally relaxed to the very small value we observe. This would solve the fine-tuning problem elegantly. We don't need to explain why the number is so small today, because it was simply always destined to become small through its own dynamical evolution. The field's current state is a consequence of its history, not a miraculously precise initial condition. This idea connects the fate of the cosmos directly to the dynamics of a specific quantum field, making the acceleration of the universe not a static feature but an unfolding process, a chapter in a much longer story written by the fields themselves. Furthermore, the mechanism of supersymmetry, if it exists in nature, offers a beautiful natural cancellation. In a perfectly supersymmetric world, every boson has a fermionic superpartner. The zero-point energy contributions from bosons are positive, while those from fermions are negative. In an unbroken supersymmetric state, these contributions would cancel each other out exactly, yielding a vacuum energy of zero. While we do not live in a manifestly supersymmetric universe, if we did, particles and their superpartners would have the same mass, which they clearly do not. It's possible that supersymmetry is a property of nature at very high energies, broken at the lower energies of our everyday world. This breaking could be just imperfect enough to leave behind the tiny, residual vacuum energy we observe as the cosmological constant. In this view, the incredible weakness of gravity and the smallness of dark energy are two sides of the same coin, both arising from the same underlying supersymmetric structure of the quantum fields at the highest energies, providing a unified and elegant solution to two of physics' greatest puzzles. Now, let's explore a secret that reveals a hidden layer of gravity's influence, one that operates not through force or curvature, but through a subtle, ghostly potential that can reach across space and alter the quantum world without ever touching it. This is the gravitational Aharonov-Bohm effect, a concept that sounds esoteric but fundamentally challenges our classical intuition about how forces work. To grasp its significance, we first need to revisit its more familiar electromagnetic cousin. Imagine a long, hollow cylinder with a powerful magnetic field confined entirely inside it, completely shielded so that outside the cylinder, there is no magnetic field whatsoever, no force, no detectable influence. Now, fire a beam of electrons toward this cylinder, splitting it so that one part of the electron wave goes around the left side of the cylinder, and the other part goes around the right. According to classical physics, since there is no magnetic field outside the cylinder, the two electron paths should be completely unaffected. They should reunite on the other side and show no interference. But in the quantum world, something astonishing happens. The electrons are affected. Their quantum wave functions acquire a phase shift, a change in their rhythm that depends on the magnetic field hidden inside the cylinder, even though they never pass through any field themselves. This is the electromagnetic Aharonov-Bohm effect, and it proves that in quantum mechanics, the electromagnetic potential, a mathematical object that describes the field's underlying influence, is more fundamental than the field's strength itself. The electrons are sensitive to this potential, this ghost in the machine, and it alters their behavior in a detectable way. This leads us to a breathtaking question. If this is true for electromagnetism, could it also be true for gravity? Could there be a gravitational Aharonov-Bohm effect? In Einstein's general relativity, we are used to thinking of gravity as the curvature of space-time, a geometric field that directly tells objects how to move. But what if, beneath that geometry, there is also a gravitational potential? a more fundamental entity that can influence quantum particles even in regions where the curvature of spacetime is zero. The proposal is that a massive object could create a gravitational potential that extends into surrounding space, and even in areas where the gravitational force is undetectable. Where spacetime is perfectly flat, this potential could still cause a phase shift in the wave function of a passing quantum particle, like a neutron or an atom. It would be a gravitational whisper, an influence without a force, a testament to gravity's hidden quantum aspect. Detecting such an exquisitely subtle effect is a monumental challenge, but it is not beyond the reach of modern experimental ingenuity. The most promising avenue involves atom interferometry, a technology we've discussed that is essentially the most sensitive ruler ever conceived. In a proposed experiment, a massive, dense object, perhaps a sphere of tungsten or lead, would be placed near one path of a split atomic beam. The setup would be carefully designed so that the atoms never pass through a region where the gravitational force is significant. They travel through a volume of space where the gravitational field gradient is essentially zero. However, they would be moving through the gravitational potential created by the mass. If the gravitational Aharonov-Bohm effect is real, the atoms traveling along the path closer to the mass would have their quantum phase subtly shifted compared to their partners on the other path. When the two atomic waves recombine, this phase difference would manifest as a shift in the interference pattern, a telltale fingerprint of the potential's influence. The beauty of this experiment is that it would test gravity in a completely new regime. It's not about measuring a force or a curvature. It's about probing a deeper, more fundamental layer of gravitational reality. A positive result would be revolutionary. It would provide direct, empirical evidence that gravity must be described by a potential in quantum theory, just like the other fundamental forces. It would demonstrate that gravity has a truly quantum mechanical aspect that operates even in the absence of a classical field, forcing a profound revision of how we think about its nature. It would be a crucial step toward proving that gravity cannot be purely classical, that it must ultimately be quantized, woven into the same quantum tapestry as the rest of physics. This tiny phase shift, measured in a highly controlled laboratory, could be the thread that finally pulls the quantum nature of gravity into the light. For all its profound mystery, dark matter presents us with a strangely simple set of clues. We cannot see it, but we can watch its gravitational handiwork everywhere we look. It bends the path of light around galaxies in a phenomenon called gravitational lensing. It dictates the rotation speeds of stars that would otherwise fly into the void. And it provides the invisible scaffolding for the vast cosmic web. We know it has mass, and therefore it interacts gravitationally, but it does not absorb, reflect, or emit light, and it seems to shy away from the strong and weak nuclear forces that govern the atomic world. This has led to a decades-long hunt for a new, exotic particle that could explain its nature, with most efforts focused on hypothetical entities known as WIMP, weakly interacting massive particles. These particles would be part of our standard quantum field framework, interacting through the weak nuclear force, albeit very feebly. Yet, despite immense and sophisticated searches deep underground and in space, these WIMP have stubbornly refused to appear, forcing physicists to broaden the search and consider a far more radical possibility. What if dark matter isn't just a shy particle within our known quantum field landscape? What if it is something entirely different, a manifestation of an entirely new type of quantum field that communicates with our world through one channel and one channel only, gravity itself? This is where the secrets of quantum gravity open up a breathtaking new frontier. If gravity is indeed an emergent phenomenon, born from the entanglement of quantum fields or from information encoded on a holographic screen, then the stage of spacetime itself is dynamic and alive. Dark matter might not be a collection of particles moving on this stage, but rather a feature of the stage, a topological defect or a particular configuration in the quantum fields that make up the fabric of reality. Think of spacetime not as a smooth sheet, but as a complex, multi-dimensional tapestry. As the universe cooled from its immensely hot and dense beginning, this tapestry might have developed wrinkles, knots, or cracks. Stable, persistent structures frozen into the very geometry of the cosmos. A specific type of one-dimensional wrinkle, a cosmic string, would be an incredibly dense filament of energy thinner than a proton, but with the mass of a mountain range per centimeter. A vast, invisible network of such strings woven through a galaxy could provide the extra gravitational pull we attribute to dark matter, without requiring any new particles at all. The matter isn't dark, the geometry is complex. Another compelling candidate emerging from the heart of quantum field theory is the action. Originally proposed to solve a completely different problem in particle physics, the action has evolved into a prime dark matter suspect. Unlike the bulky WIMP, the action would be extraordinarily light and incredibly numerous, trillions of them passing through you every second without a trace. But its most fascinating property is how it is born. The action is not a particle in the traditional sense. It is the excitation of a specific quantum field that is expected to exist based on profound symmetry arguments. This field would have a very low energy and would interact with ordinary matter only through the most feeble of means, primarily through a subtle interplay with the electromagnetic field. This makes it effectively invisible, yet it would still possess mass and therefore exert a gravitational influence. Because of its wave-like nature, a cloud of actions would not behave like a swarm of discrete bullets, but more like a pervasive, sloshing fluid that fills a galaxy, its gravitational field guiding the stars within it. This idea beautifully links the extremely small, the symmetries of quantum fields, to the extremely large, the dynamics of entire galaxies. Perhaps the most profound possibility is that dark matter resides in a completely separate, hidden sector of quantum fields. Our visible universe, with all its quarks, electrons, and photons, would be just one set of vibrations in a grand cosmic symphony. There could be an entire other orchestra playing alongside ours, comprised of different quantum fields that do not interact with ours via the electromagnetic or nuclear forces. The only instrument both orchestras share is the gravitational field. Vibrations in these hidden fields would be completely invisible to us, yet their energy would curve spacetime, creating the gravitational effects we see. In this view, dark matter isn't something rare or exotic. It could be the majority of the universe's content, living right alongside us in a parallel reality that is forever beyond our direct sight, connected only by the universal language of gravity. This suggests a cosmos of stunning depth and complexity, where what we see is merely a fraction of what exists, and the force of gravity is our only window into the hidden depths of reality. But as we probe the limits of the quantum world, we encounter a paradox so deep it calls into question the very nature of reality itself, the infamous measurement problem. In the bizarre rules of quantum mechanics, a particle like an electron doesn't have a definite position or spin until it is measured. It exists in a ghostly superposition, a blend of all possible states. Yet, the moment we observe it, this fuzzy cloud of probabilities seems to instantly snap into a single, definite reality. The act of measurement itself appears to trigger this transition, but the theory is completely silent on what actually constitutes a measurement or why it causes this collapse. Is it the interaction with a conscious observer? The act of recording data? Or is it something more fundamental, woven into the fabric of the universe? This has been a philosophical quagmire for nearly a century, but what if the solution isn't in the realm of consciousness or information, but in the force that sculpts the cosmos? What if gravity itself is the universal arbiter of reality, the hidden hand that forces the quantum world to make up its mind. This is the radical proposal put forward by the renowned physicist Sir Roger Penrose. His objective collapse theory suggests that wave-function collapse isn't a random event or a consequence of observation, but a spontaneous, physical process driven by the particle's own gravitational field. The idea hinges on a profound concept: gravitational self-energy. In Einstein's view, energy and mass are equivalent, and all energy curves space-time. A particle in a superposition isn't just in two places at once. Its mass is also in two places at once. This means it exists in two different gravitational states simultaneously, creating a superposition of spacetimes, a kind of blistering in the fabric of reality where the geometry itself becomes undefined. Penrose argues that this situation is inherently unstable. The universe has a kind of intolerance for such ambiguity in its own geometry. This conflicting spacetime curvature generates a tiny but real energy difference between the superposed states. Given enough time, this energy difference builds up until the system reaches a threshold and spontaneously collapses into one definite state, simply because maintaining the superposition becomes energetically unfavorable. The gravitational field of the object itself acts as its own observer, forcing a choice to resolve the cosmic confusion. In this breathtaking model, the quantum fields we've discussed throughout our journey would play the crucial role of the mediator. The immense energy required to sustain a warped, superposed spacetime would be stored in the configuration of these fields. Their fluctuations would be what ultimately becomes too unstable to maintain, and their sudden reorganization into a single, classical state would be the physical mechanism of the collapse. It's a process where the quantum fields and the geometry of spacetime are in a constant dialogue, with gravity imposing a classical order on quantum chaos. The larger the mass of the object, the greater its gravitational self-energy, and the faster this collapse occurs. For a tiny electron, superposition could last for millions of years. But for a macroscopic object like a cat or a measuring instrument, the collapse would be instantaneous, explaining why we never see such quantum weirdness in our everyday world. The boundary between the quantum and classical realms isn't drawn by size, but by the gravitational influence of an object on the structure of spacetime itself. While Penrose's idea is mathematically elegant and profoundly compelling, it remains highly speculative and faces significant challenges. The predicted collapse times for most objects are currently far too quick to be tested with today's technology, and the theory has not yet been fully integrated into a complete mathematical framework of quantum gravity. However, its power lies in its audacity to provide an objective, physical solution to a problem that has long been mired in philosophy. It forges a direct link between the two great unsolved puzzles of physics, the nature of quantum measurement and the quantum nature of gravity, suggesting they are not separate issues but two aspects of the same profound truth about our universe. It proposes that the force that holds the planets in their orbits and gives weight to our world is also the silent architect of reality, continuously working behind the scenes to crystallize possibility into actuality, ensuring the world we experience is solid, definite, and real. Imagine the very first moment of our universe, a realm of such incredible energy and density that the very concepts of space and time as we know them begin to blur. In this primordial fireball, a monumental event was set into motion, an event that would dictate the fate of everything to come. This is the theory of cosmic inflation, a period of staggeringly rapid exponential expansion that occurred within the first tiny fraction of a second after the Big Bang. In an almost unimaginably short burst, the universe increased in size by a factor of at least 10 to the 78th power, smoothing and flattening the cosmos in an instant. For decades, the driving engine behind this incredible growth was a profound mystery. What force could possibly be so powerful, so dominant, that it could overwhelm all others and stretch the fabric of reality itself so violently? The answer, it turns out, lies not in a force at all, but in a field. A specific, hypothetical quantum field known as the inflaton field is thought to have permeated all of space, and its unique properties are what powered the universe's most dramatic growth spurt. Think of the inflaton field like a vast, rolling landscape of energy. In its highest, most energetic state, this field possessed a peculiar characteristic. It exerted a tremendous negative pressure. Unlike anything we experience in our everyday world, this negative pressure acted as a kind of repulsive gravity, causing space-time itself to expand at an accelerating rate. It's as if the universe was stuck on a high plateau on this energy landscape, and while it was there, its expansion was driven by the immense energy density of the field. This inflationary period didn't last forever. Like a ball slowly rolling down a hill, the inflaton field eventually lost energy, decaying from its high energy state and settling into a lower valley. As it rolled down, the energy that had been stored in the field was released in a tremendous burst, flooding the universe with particles and radiation, reheating it into the hot, dense soup of the conventional Big Bang. But the most breathtaking part of this story is not the expansion itself, but what was happening on an unimaginably tiny scale during this explosive event. The same quantum rules that govern particles were also governing the inflaton field, and this had consequences that would echo for billions of years. Even during inflation, the inflaton field was subject to the fundamental uncertainty principle. It was constantly fluctuating, jittering with quantum uncertainty. At these infinitesimal scales, virtual particles representing slight variations in the field's strength were constantly blinking in and out of existence. In the ordinary, slow-moving universe of today, these fluctuations are tiny and transient. But during inflation, something extraordinary happened. The expansion of space was so rapid that it stretched these microscopic quantum fluctuations in the inflaton field to astronomical sizes. A tiny ripple in the field that was smaller than a proton one moment could be stretched to the size of a galaxy cluster in the next instant. Once these fluctuations were stretched beyond the horizon, the distance light could have traveled in that time. They were effectively frozen into the fabric of the universe. They became permanent, classical imprints on the cosmos. These frozen ripples in the inflaton field translated directly into tiny differences in the density of matter and energy across space. Where the field was slightly more energetic, a little more matter would be created after reheating. Where it was slightly less energetic, a little less matter would form. These tiny density variations, born from quantum jitter and magnified by inflationary expansion, are the seeds of all structure in the universe. They are the gravitational nurseries for everything we see. Over the next 13.8 billion years, gravity got to work on these seeds. Regions with a tiny bit more mass had slightly stronger gravity, pulling in more matter from their surroundings. This made them even denser, pulling in even more matter, in a powerful feedback loop that eventually led to the formation of galaxies, stars, and planets. The entire cosmic web of dark matter and galaxies that we observe today with our telescopes is a direct result of these quantum fluctuations written across the sky. This means that the largest structures in the universe, great clusters of galaxies stretching for millions of light years, have their origin in the probabilistic, fuzzy laws of the quantum world. The pattern of the cosmos was born from quantum uncertainty, but the story doesn't end with matter. The same violent, rapid expansion of spacetime during inflation would have also excited the gravitational field itself. According to Einstein's theory, accelerating masses produce ripples in spacetime called gravitational waves. The incredible acceleration of the universe during inflation would have been the most powerful generator of gravitational waves imaginable. Quantum fluctuations in the spacetime metric The very geometry of the universe would have been stretched from the microscopic quantum realm to macroscopic scales, creating a background sea of primordial gravitational waves that still permeates the universe today. These waves are a direct prediction of the inflationary paradigm and would provide a unique, smoking gun signature of the event. Their detection would be like hearing the echo of the Big Bang itself. Furthermore, these gravitational waves would have interacted with the light from the primordial universe, leaving a distinct, twisting pattern called B-mode polarization in the cosmic microwave background radiation. Hunting for this faint fingerprint in the ancient light of the cosmos is one of the primary goals of modern observational cosmology. Finding it would not only confirm inflation, but would also provide a direct link between the quantum fluctuations of the gravitational field and the large-scale structure of the universe we see today, beautifully connecting the quantum world to the cosmic scale through the most fundamental force of all. Imagine you are an astronaut, courageously plunging toward the event horizon of a black hole. According to Einstein's cherished equivalence principle, this should be a serene, even boring experience. Since you're in free fall, you should feel weightless, floating effortlessly in the void. The event horizon itself should be invisible and intangible, a point of no return you cross without even noticing anything special happening. For decades, this was the accepted and elegant picture. But a devastating thought experiment, born from the clash between quantum mechanics and general relativity, has shattered this peaceful image, suggesting that instead of a quiet crossing, you would be instantly vaporized by a searing wall of energy, a black hole firewall. This paradox isn't just a quirky puzzle. It's a direct assault on our understanding of reality, forcing us to choose between the foundational pillars of modern physics. The roots of this inferno lie in the seemingly benign phenomenon of Hawking radiation. As we've explored, quantum fields near the event horizon allow for pairs of virtual particles to appear. Normally, they annihilate each other almost instantly, but at the horizon, one can fall in while the other escapes, becoming real radiation. This process slowly steals mass from the black hole. To preserve the fundamental quantum rule that information cannot be destroyed, the escaping radiation must be subtly entangled with the particle that fell in. This entanglement is the cosmic glue that ensures the information about what fell into the black hole is eventually encoded in the outgoing radiation. However, here's where the plot twists into a paradox. Quantum mechanics has another unbreakable rule, the monogamy of entanglement. A single particle cannot be fully entangled with two different things at the same time. This sets up an impossible conflict. Consider three particles, the escaping Hawking particle A, its partner that fell in long ago B, and a new Hawking particle C just now escaping with its own partner D. For information to be preserved, particle A must be entangled with its old partner, particle B. But for the radiation to look thermal and random to a distant observer, particle A must also be entangled with the new particle C. It simply can't be maximally entangled with both. To resolve this, the laws of quantum mechanics demand that the entanglement between A and B must be severed as the new radiation is emitted. But severing quantum entanglement is a violent, energetic process. It releases a tremendous amount of energy. This energy would manifest not as a gentle glow, but as an incredibly intense, energetic barrier right at the event horizon, a firewall. Any astronaut crossing the horizon wouldn't experience a smooth descent into darkness. They would be instantly incinerated by this wall of fire, a region of chaotic, high-energy particles. The implications of this are staggering. The firewall paradox forces us into a trilemma, a choice between three deeply unpalatable options, each of which breaks a fundamental law of physics. First, we could accept that black holes have firewalls, incinerating anything that falls in. But this completely violates Einstein's equivalence principle. the very cornerstone of general relativity, which guarantees that crossing the horizon is an uneventful experience for someone in free fall. Second, we could deny that information is preserved in Hawking radiation, allowing it to be lost forever. But this would violate unitarity, a sacred principle of quantum mechanics that says information can never be truly destroyed. The third option is to deny the monogamy of entanglement itself, which would require a radical and likely impossible rewriting of the entire framework of quantum mechanics. We are left with no good choices, each one demanding we sacrifice a theory that has been exquisitely confirmed by experiment for a century. This paradox is not a sign that our theories are broken. It is a powerful signal that they are incomplete. It is the universe's way of screaming that we cannot successfully describe the most extreme environments by patching together quantum field theory and general relativity. They must be replaced by a deeper, more unified theory of quantum gravity. The firewall highlights a profound inconsistency in our description of the vacuum around a black hole. In Einstein's view, the vacuum is smooth and empty at the horizon, but the quantum field description says it is a frothing, energetic sea of particle creation. The firewall is the physical manifestation of this disagreement. It tells us that our concept of spacetime itself, especially at a boundary as exotic as an event horizon, cannot be trusted. The smooth, continuous geometry of general relativity must break down, giving way to some new quantum structure that we do not yet understand. The debate rages on, with physicists fiercely advocating for different resolutions. Some, like the proponents of black hole complementarity, suggest that the experience of the astronaut and the distant observer are both correct in their own frames of reference, and that no single observer can ever see both the smooth horizon and the violation of monogamy, thus preserving consistency. Others are exploring ideas like ER equals EPR, which suggests that the entangled particles are connected by tiny wormholes, potentially allowing for a kind of entanglement that doesn't violate monogamy in the traditional sense. The firewall paradox is not an end, it is a beginning. It is a crucible forging new ideas and forcing us to confront the deepest questions about information, entanglement, and the very nature of spacetime, proving that even our most brilliant ideas must evolve when faced with the ultimate extremes of nature. Why does time have a direction? In our daily lives, the arrow of time seems obvious and absolute. We remember the past, we anticipate the future, and we watch as spilled milk never unspills and shattered glass never reassembles itself. This relentless march from past to future is so ingrained in our experience that we take it for granted. Yet, the fundamental laws of physics, from Newton's mechanics to Einstein's relativity and even the Schrödinger equation, are almost entirely time-symmetric. They work just as well if you run the film of the universe backward. So where does this powerful, one-way arrow come from? The answer may lie not in the laws that govern particles and forces, but in the unique, special conditions of our universe's birth conditions that were dictated by the mysterious interplay of quantum gravity. To understand this puzzle, we need to look at the concept of entropy, which is the physicist's measure of disorder. The second law of thermodynamics states that the total entropy of a closed system always increases over time. It's this statistical tendency toward disorder that explains why your clean room gets messy, and why heat flows from a hot cup of coffee to the cooler room. The arrow of time in this view is simply the direction in which entropy increases, but this just pushes the question back a step. Why was the entropy of the universe so incredibly low in the first place? Why did our cosmos begin in a state of exquisite order, a tightly wound spring that has been uncoiling and becoming more disordered for 13.8 billion years, creating the familiar flow of time we all experience? This is where quantum gravity and the Big Bang enter the story with a breathtaking proposition. The initial state of the universe wasn't just any state, it was a quantum gravitational state. The incredible density and energy of the Big Bang meant that the very concepts of space and time were being born from a more fundamental, pre-geometric reality. In this fiery forge of creation, the laws of quantum gravity would have been the dominant rules. Some theories, like the Wheeler-DeWitt equation, suggest this initial state was fundamentally timeless. So how did time emerge? One compelling idea is that the direction of time was set by a process called quantum decoherence acting on a cosmic scale. Imagine the entire newborn universe as a single, unified quantum system in a pure, coherent state, a superposition of many possible configurations. But a system that large and complex couldn't stay coherent for long. Its countless parts would inevitably interact with each other, causing this pristine quantum state to decohere, to collapse into a more classical, definite reality. This decoherence process would have happened in a specific direction, effectively choosing one timeline out of a fog of quantum possibilities. The moment the universe decohered from a quantum blur into a classical state with a specific, low-entropy configuration, the die was cast. The arrow of time was fired. From that point on, the only statistical direction for the universe to evolve was toward higher entropy, creating the irreversible past-to-future direction we all experience. In this view, the arrow of time is not a fundamental law written into the cosmos. It is a historical accident, a fossilized remnant of the universe's quantum gravitational origins. The reason we remember the past, and not the future, is because the past is the state from which our universe decohered, a unique moment of order from which all disorder flows. An even more profound possibility comes from the application of boundary conditions to the entire cosmos. In physics, to solve any equation, you need to specify the conditions at the boundary. For the universe, the ultimate boundary is its beginning. The no-boundary proposal, put forward by James Hartle and Stephen Hawking, offers a specific quantum gravitational condition for the start of the universe. It suggests that if we could run the clock backward to time equals 0, the character of time would change, smoothly transforming into a dimension that behaves more like space. In this model, there is no sharp, singular beginning, no boundary. This specific, smooth initial condition automatically selects for a universe that starts in a state of very high order and low entropy. It's the only way for the universe to be self-consistent according to the laws of quantum gravity. The arrow of time, then, is baked into the very geometry of the cosmos at its origin. It is the inevitable consequence of the universe having no other boundary than this smooth, self-contained start. The past is different from the future because the universe began in this particular way, and the relentless increase of entropy is just the unfolding of that initial quantum gravitational state. Our experience of time's flow is our local perception of the universe gradually exploring all the possible disordered states that were made available to it at the moment of its creation. We have journeyed through secrets that reimagined gravity as an emergent force, a holographic projection, and a thermal phenomenon. But what if we were to take the final, most radical step? What if the very stage upon which this cosmic drama unfolds, space-time itself, is not a fundamental entity, but a secondary collective illusion? This brings us to the breathtaking 37th secret, an idea that proposes the geometry of the universe, the very arena of reality, is woven into existence by the most counterintuitive property of the quantum world, entanglement. To grasp this, let's start with a simple but profound question. What is distance? We think of it as the measurable space between 2 points. But in the quantum realm, 2 particles can be entangled, meaning their fates are linked instantaneously across any distance, as if the space between them doesn't exist for their connection. This spooky action at a distance suggests that quantum correlation operates on a level deeper than space-time. It hints that space is not the primary medium through which particles interact. Rather, the interactions themselves might be what create the concept of space. Think of it like this. Imagine a vast, dark room filled with people who cannot see each other. Now, give every person a partner and have them hold a synchronized stopwatch. Even in total darkness, the synchronized partners share a connection, a correlation, that exists independently of the physical space between them. The space is still there, but their connection transcends it. Now, imagine that the space itself, the room, is actually generated by the web of all these synchronized relationships. This is the core of the idea that space-time emerges from entanglement. This revolutionary concept is often captured by the slogan, "It from bit," coined by physicist John Archibald Wheeler. It proposes that what we perceive as physical reality, the it of particles and forces, ultimately derives from information, the bit. In this view, the fundamental ingredients of the universe are not tiny strings or grains of space, but abstract quantum bits of information and their interconnections. Entanglement is the most powerful form of quantum information correlation, creating a vast, complex network of relationships. The stunning proposal is that the geometry of spacetime, its curvature, its distances, its very structure, is a direct representation of the pattern and strength of entanglement between these underlying quantum bits. The mathematics behind this is elegant and compelling. Physicists have discovered that the amount of entanglement between two regions of space is directly related to the area of the boundary separating them. This is eerily reminiscent of the black hole formula where entropy is proportional to area, not volume. It suggests that the surface area between 2 points is what's fundamental, and the volume, the space we experience, is a derived concept. The more entangled two regions are, the more connected they are, and the closer they are in an informational sense, which then manifests as them being physically closer in the emergent spacetime geometry. Gravity, in this picture, is not a force that travels through space. Instead, it is the dynamic manifestation of changes in this cosmic entanglement network. When masses move, they are not warping a pre-existing stage. They are altering the entanglement patterns of the underlying quantum bits, and the stage reconfigures itself accordingly. The gravitational attraction we feel is the universe's tendency to maximize the entanglement entropy between objects, pulling them into a state of greater quantum connectedness. This provides a stunningly unified vision of reality. The quantum fields we've discussed throughout our journey are not in spacetime. They are the entities whose entangled states give rise to spacetime. The force of gravity is the story of how this tapestry of connection weaves and reweaves itself. It suggests that the cosmos is not a container that holds things, but a network of relationships that creates the illusion of a container. The solid ground beneath your feet, the vast emptiness between stars, the curvature around a planet, all of it is a magnificent, dynamic hologram projected from a deeper, more fundamental layer of quantum information, where everything is connected, and the geometry of existence is written in the language of entanglement. And so we arrive at the culmination of our journey, the final and most profound of the 38 secrets, a vision of reality so elegant and complete that it seeks to weave every thread we've explored into a single, magnificent tapestry. This is the dream of a theory of everything, a final synthesis where the quantum fields are not merely the actors on the stage of spacetime, but are the very substance from which the stage, the actors, and the play itself are all woven. In this ultimate framework, gravity is not a force that must be awkwardly added to the quantum picture. It is an inherent, emergent property of a deeper, unified reality. It is the final piece of a cosmic puzzle, not because it is the most important, but because its successful inclusion is the signature that the puzzle is finally complete. For decades, the holy grail of physics has been to find this single, overarching mathematical principle that describes all forces and all matter under one roof. The standard model of particle physics is a masterpiece, but it is a catalog of parts, not a unified design. It describes three of the four fundamental forces: electromagnetism and the strong and weak nuclear forces, with breathtaking accuracy, but it leaves gravity out in the cold, governed by the completely different classical rules of general relativity. A true theory of everything would erase this artificial divide. It would reveal that the electron and the graviton, the quark and the photon, are all different vibrations of a single fundamental entity. Imagine a vast, silent ocean. The waves on its surface can take many forms: tiny ripples, powerful rolling swells, even complex, crossing patterns. To an observer who only understands waves, these might seem like different phenomena. But they are all just water, moving in different ways. A theory of everything would be the discovery of the water itself, the single, fundamental substance whose various vibrations manifest as all the particles and forces we see. One of the most ambitious and mathematically sophisticated candidates for this role is M-theory, a development arising from the earlier frameworks of string theory. Its central, beautiful idea is that at the most fundamental level, the universe is not composed of point-like particles. Instead, the basic ingredients are unimaginably tiny, one-dimensional vibrating strings and their higher-dimensional cousins, called branes. The different vibrational modes of these strings, how they wiggle and resonate, determine whether they manifest as an electron, a photon, or a quark. In this framework, the graviton, the hypothetical carrier of gravity, would simply be a specific, quiet vibration of a closed string. This is the profound unification we seek. Gravity is not a separate force. It is just another note in the same cosmic symphony, played on the same instrument as everything else. M-theory then takes this a step further by proposing that these strings exist in an 11-dimensional reality. The 7 extra dimensions are curled up into fantastically small, complex shapes at every point in space, and the specific geometry of these hidden dimensions determines the properties of the forces and particles we observe in our 3-dimensional world. The strength of gravity, the mass of the electron, the charge of the quark, all would be fixed by the shape of this hidden geometry, making our entire universe a unique and fascinating solution to a much deeper, multi-dimensional equation. The implications of achieving such a synthesis are almost beyond comprehension. It would represent one of the greatest intellectual achievements in human history, a moment where our species deciphered the basic source code of the cosmos. But its power would extend far beyond mere understanding. A true theory of everything would be a predictive engine of unimaginable power. It could allow us to peer back past the Big Bang to understand the true origin of the universe, or to model the final fate of matter inside a black hole's singularity without our equations breaking down into infinities. It could reveal if other universes with different physical laws are not just possible, but inevitable, placing our own cosmic home within a vast multiverse. On a more practical, though distant, level, the deep understanding of space-time and quantum fields it provides could unlock technologies that sound like pure science fiction, mastery over gravity itself, or the ability to manipulate the topology of space-time. More immediately, the journey to discover it has already revolutionized mathematics and our understanding of quantum information, proving that the quest itself is as valuable as the destination. Yet, for all its grandeur, we must also embrace a note of profound humility. Even if we were to discover the perfect, final equation tomorrow, it is unlikely to simplify our daily experience of the world. The universe described by a theory of everything would be the fundamental, microscopic reality. The world we live in, the world of trees and planets and people, is an emergent reality, a complex and beautiful pattern that arises from the collective behavior of those fundamental parts. Knowing the equation for water does not make the phenomenon of a hurricane any less complex or awe-inspiring. In the same way, a theory of everything would not render other sciences obsolete. It would instead provide the ultimate foundation upon which they are built. It would be the fundamental law from which chemistry, biology, and ultimately consciousness itself emerge. This is the true meaning of the final secret. Unification does not mean reduction. It means connection. It shows us that every force, every particle, every moment of time and fragment of space is deeply, inextricably linked, part of a single, unfolding story written in the language of quantum fields. Our journey through these 38 secrets has been a journey toward that wholeness, a step toward seeing the universe not as a collection of separate mysteries, but as one magnificent, coherent whole. So after this incredible journey through 38 profound secrets, what are we left with? A scattered collection of interesting ideas or something far greater? The true power of these insights isn't in their individuality, but in the breathtakingly cohesive picture they form when woven together. We began by questioning the very nature of gravity, and we end with a radical new vision. Gravity is not a fundamental force. It is an emergent phenomenon, a collective illusion born from the complex dance of quantum fields. It is thermal, a thermodynamic force driven by entropy and information. And it is holographic, a projection from a lower dimensional reality where the true laws of physics reside. Think of it like the phenomenon of wetness. If you were an intelligent water molecule, you would understand your own properties, your mass, your bonds with other molecules, but the concept of wetness would be completely foreign to you. Wetness isn't a property of any single water molecule. It is an emergent property that only appears when trillions upon trillions of molecules interact in a specific way. In exactly the same manner, gravity appears to be an emergent property. No single quantum fluctuation, no single entangled particle pair possesses gravity. But the collective, statistical behavior of all of them, the way they store information, maximize entropy, and correlate with one another, manifests as the force that shapes the cosmos. This is why gravity feels so different from the other forces, because it is different. It's not a force at all in the traditional sense. It's a side effect, a cosmic mirage. This synthesized view doesn't just add a new chapter to physics. It resolves some of the most stubborn paradoxes that have plagued us for decades. The black hole information paradox, which pitted quantum mechanics against general relativity, melts away when we see the event horizon not as a deadly boundary, but as a holographic screen storing information. The firewall vanishes when we understand that entanglement and wormholes are two sides of the same coin, preserving the purity of the vacuum for a freely falling observer. The haunting discrepancy of the cosmological constant begins to make sense when we stop thinking of vacuum energy as a source that curves space-time and start seeing it as the very substance from which space-time is built. These aren't just isolated solutions. They are different facets of the same diamond, each reflecting the core truth that gravity emerges from quantum information. The elegance of this new paradigm is its incredible predictive power. It's not just a beautiful story. It's a framework that guides us toward new experiments and new discoveries. It tells us to look for the faint whispers of quantum gravity not only in the collisions of black holes, but in the delicate jiggling of atoms in a Bose-Einstein condensate, in the precise timing of distant pulsars, and in the ancient light of the cosmic microwave background. It predicts specific signatures, certain patterns in gravitational wave echoes, specific types of noise in quantum interferometers, distinct twists in the polarization of the universe's first light that can confirm or refute its proposals. This is the mark of a robust scientific revolution. It doesn't just explain what we already see. It shows us where to look next and what we might find. Ultimately, this synthesis points us toward a theory of quantum gravity, but not in the way we initially imagined. We are not finding a graviton particle that fits neatly into the standard model. Instead, we are discovering that the search for quantum gravity was a misdirection. We don't need to quantize spacetime because spacetime itself is quantum. It emerges from the quantum. The goal is not to make gravity quantum, but to understand how quantum mechanics gives rise to gravity and geometry. This flips the entire problem on its head. We are not building a bigger cage to house gravity. We are realizing that gravity was never in the cage to begin with. It is the cage, and we are now learning how it is constructed from more fundamental quantum parts. This new vision of gravity is more strange and magnificent than any force, inviting us to see the universe not as a space-time arena with actors, but as a dynamic, evolving network of information from which the very idea of an arena spontaneously appears. We have journeyed together through a cosmos of ideas, from the restless quantum foam at the smallest scales to the holographic projection of our entire reality. And what we are left with is not just a new theory of gravity, but a new way of seeing the universe itself. Gravity is no longer that simple, familiar pull described by Newton, nor is it merely the curvature of spacetime from Einstein's brilliant mind. It is something far more marvelous and strange, a thermodynamic force, an entropic gradient, a geometric illusion woven from the deepest quantum connections that bind everything together. Each of these 38 secrets is a vital piece of this grand puzzle, a step on the path toward the final unification of physics. They show us that the universe is not a collection of separate parts, but a single, interconnected whole, where the force that guides the planets is born from the same quantum magic that governs the smallest particles. This journey doesn't end here. It simply opens a new door. Every one of these profound ideas started as a spark of curiosity in the mind of a scientist daring to ask what if. That same curiosity is what fuels this channel and, we hope, fuels your own wonder about the cosmos. Your engagement, your questions, and your passion for understanding are what turn these complex theories into a living, breathing conversation. We want to hear which of these secrets resonated most with you. Did the holographic principle bend your mind? Does the idea of emergent spacetime change how you see the world around you? Share your thoughts in the comments below. Let's continue this exploration together. If you want to join us as we dive into the next great mystery, make sure to subscribe and hit the bell so you don't miss our future deep dives into the frontiers of physics and astronomy. The universe is full of wonders waiting to be uncovered. From the nature of dark matter to the possibility of other dimensions, the next revolutionary discovery, the one that finally cracks the code of quantum gravity, might be just a moment away. It could be happening in a lab right now, or being scribbled on a whiteboard, or perhaps it's waiting for you to have that one brilliant insight. So stay curious, keep looking up at the stars and down into the quantum depths, and remember that the greatest force in the universe isn't gravity,